Hello and welcome to Reverse Engineering Kata for Beginners. Hi, I am Paul Chin and I'm your instructor for this course. If you are completely new to Kata and want to quickly learn how to use this tool, then this course is for you. You will learn how to use Kata on Windows and also Linux. By the end of this course, you will be able to use Kata to do static and dynamic analysis, debug and patch binary files, fish for serial keys, passwords, and more. Kata is a free and open source tool for reverse engineers. It is a disassembler, decompiler, and also a debugger. Also, all tools used in this course are free and open source. What you will learn. In this course, we will cover static and dynamic analysis, how to disassemble, decompile binary files, analyze the stack, registers, and to inspect memory using hex dumps, reverse jumps using no-ops to disable instructions, modify instructions and patch binary files, understanding Windows API, C++ functions and assembly language, differences between 32-bit and 64-bit registers and binary files, string searches, password and serial key phishing, doing graphical and linear view analysis, defining functions, renaming variables and functions, using the reason console and also the debugging console, stepping over and stepping into and out of function calls, and more. Who this course is for? This course is intended for reverse engineering and malware analysis students. It is also for anyone interested to learn to use Kata for reverse engineering. Prerequisites. For this course, we will need a Windows PC. Some knowledge of basic assembly and C language will be helpful, but not strictly necessary. Also, some basic Linux commands will be useful, although it is not strictly necessary. All you need to know will be covered in this course. My background. By profession, I'm a retired college lecturer and I've been teaching computer science and IT for more than 20 years. And I welcome you to this course. See you inside. Hello and welcome. In this video I'm going to show you where to download Cutter and how to install it. So go to this website here, cutter.re, and this is where you can get your Cutter program. There is a button, download button, just click on it to begin the download process. So now the download has begun, just let it complete. Now it has finished downloading. Just go to the folder where it was downloaded to, the downloads folder, and unzip it. So right click and unzip it using your favorite unzipper. Now it has created a new folder. After unzipping, just open it and you will see all the files are inside it. So we are going to cut it and put it in your favorite location. I'll put it in my tools folder. Just right click and paste it here, or just Ctrl V. So now I'm going to create a desktop shortcut. So open the folder for Cutter and then right click on the Cutter exe, drag, right click drag to the desktop and select create shortcuts here. So now you can see you have already created a new shortcut on the desktop. So now let us test the shortcut. Double click on it. And the Cutter dialog opens up. And over here you can see that there are some customization possible. You can change your theme. The default is native theme, and I will leave it as the default. Then click on the continue button, and now your Cutter is ready for use. So this is how you download and install Cutter. That's all for this video. Thank you for watching. Hello and welcome. In this video I'm going to give you a few tips on how to do reverse engineering using Cutter. First of all, I want to advise you to use a virtual machine. Over here I'm using Oracle VirtualBox, which you can download for free and install it. And then after that, install Windows 10 inside your VirtualBox. So here you can see I have Windows 10 virtual machine is running. So the advantage of this is that whenever you want to do any kind of reverse engineering or even malware analysis for that matter, you will always use your virtual machine. Alright, and then if you are doing reverse engineering, some of the crackmes you download, you do not know whether they are malicious or not. So sometimes when you download, you might scan it with your antivirus and it says it's malicious, but actually it's false positive. But still you cannot be 100% sure. So that is why you should always use virtual machine for peace of mind. So the advantage of virtual machine, if you have used one before, is that after you have done some analysis, you can always revert back to the previous state. So if there's any malware, it will automatically be removed. So notice that I've installed Cutter and I've created a snapshot of the Cutter. So after installing Cutter in my virtual machine, I make a snapshot. And then after that, I will go and download any crackmes into my virtual machine. This is my virtual machine. So my Cutter is here. I will download crackmes, put it here, and I can have peace of mind knowing that even if this is malicious, I'm protected because it's a virtual machine. So always use a virtual machine. Alright. So I've installed Cutter, and in here from the previous lesson I've showed you how I did it. So now I want to show you where to get your crackmes. So crackmes are files written for practicing reverse engineering, we do not use real commercial software because that would be illegal, and Udemy also will not allow that. So we can only use CrackMe's for learning reverse engineering. So there are many sources of CrackMe's, and for starting off, go and download this CrackMe called 01 CrackMe zip from the resource section for this lesson. After you download it, put it in a folder. For me, I created a folder CrackMe's on my desktop, and I put it inside there. And then you unzip it. So to unzip it, just unzip it like this. There will be a password. So the password is crackinglessons.com. Right, crackinglessons.com. Click OK. So now it is unzipped. You can find your CrackMe inside here. Now, for this course, I'll be using CrackMe's written by other people, and also some of them are written by myself. So for this particular CrackMe, it's called For CrackMe. So it's For CrackMe. I like to give credit to the authors for this CrackMe. You can get it from here. Alright, I downloaded it from here. So if you go there, this website, you can find this CrackMe, and the author's name is also there. Let me just show it to you. So I've opened my Google Chrome and head over there and show you where I download this from. So the author for this CrackMe is called Saptam. So I'm giving credit to him here. And this is a C++ CrackMe. And the Saptam shared his graciously shared his CrackMe on CrackMe's 1. So CrackMe's 1 is one of the places where you can get CrackMe's. Later on, I will show you where other places where you can get CrackMe's as well. So you don't have to download from here because I already downloaded it. So you can just use the one that I shared with you here. If you downloaded the original copy from here, then to unzip it, you need to use a different password, which is called CrackMe's 1. Okay, so this is called CrackMe. CrackMe is written for you to practice reverse engineering. Now, one thing that you will find is that many of these CrackMe's, if you were to upload them to VirusTotal or your antivirus, when you scan it, it will say it's malicious. But the truth is, most of them are false positive. They are not really malicious. So for example, if you were to upload this to anti-scan, many people like to use VirusTotal to upload their exe file, but I advise you not to use VirusTotal because even though your CrackMe is not a virus, if you upload it many times, eventually it becomes malicious, because VirusTotal has a bad reputation of sharing your exe file that you upload with other antivirus vendors, and these antivirus vendors, or somehow or other, they always label CrackMe as malicious, because to them these are unwanted programs. Unwanted means you're not supposed to learn cracking. Okay, so that's my experience to you and my advice to you. Okay, if you really have to scan with your antivirus, instead of using VirusTotal, you can try another one, which is called antiscan.me. Okay, antiscan.me, at least they do not share your files with other antivirus vendors, unlike VirusTotal. Okay, so antiscan, if you really have to check it out, you can go and upload it here. So I'm uploading this over here, and then let it scan file. So I have to choose a file. CrackMe 1. I didn't manage to upload just now, so it's there. So I click scan file. I won't be surprised if there are false positives. So I scanned this before, and they told me there are two positive. Alright, it's not showing for some reason. So they will scan it against 26 antiviruses, and 2 of it says it's malicious. Now believe me, it is not malicious. So if you were to open this in your cutter later, you can see there's nothing malicious about it at all, because nothing can hide from the reverse engineering tools. If it is malicious, you can see what the code is actually doing when you open it in the cutter. Okay, so I just want to give you these tips, so don't get alarmed if you use VirusTotal and it says it's malicious. It could be just false positive. But in any case, always to be on the safe side, please use a virtual machine. Okay, that is the best. Alright, so now let's get started. How do you open this file? I will show you in the next video. So in this video, I just want to give you these preliminary tips to get you started on where to what are crackmates, and about false positives, and also that you should be using virtual machines whenever you are learning reverse engineering or malware analysis. Okay, so that's all for this video. Make sure you go and download this and unzip it. In the next video, we will get started with the cutter user interface, where I explain to you the basic components of the user interface. Thank you for watching. See you then. Hello and welcome back. In this video, we shall explore the cutter user interface and also some preferences settings. So let's open cutter by double clicking the desktop shortcut. Over here, click on select to select the crackme that you want to open. So our crackme is located on the desktop here inside 01 crackme folder. This is the one. So just click on select and then navigate to the desktop crackmes 01 crackme and click on this and click open button. Next, click on the open button down here, and then here make sure that analysis checkbox is checked to enable the analysis, and the level is auto. Leave it at auto. And then over here, notice that you can load in write mode. So when you load in write mode, it means that you can patch the binary itself. So if you are going to load in write mode, before you do that, make sure you make a copy of this. So I'm going to make a copy over here, so that in case I made some mistake, I still have the copy of the original file. So now I can load in write mode. And then over here, after doing that, I click on the OK button. So now it's performing analysis, and once it's finished, it loads it. So on the left here, you will see all the functions that has been detected by cutter. And at the bottom, you will see some of the external functions. So these functions are external functions. They all come from this DLL file called Microsoft Visual C Runtime. So these are the libraries that are used when the programmer wrote this program. He or she used these libraries. And here it shows you the name of the functions that are used from these libraries. So you can see you have some exit function, fprintf function, memory copy, printf, scanf, and so on. So these are all C libraries. fprintf and printf are clear indications that they are C libraries, not C++. So over here you will see one of it is the main function. So the main function is where the program begins execution. And then in the center you have the main window, which is called the disassembly window. So Cutter has taken the binary and disassembled it into assembly language. So this is the assembly language that has been generated by through the analysis and disassembly. On the left is your location of the address in hex. So now we are at entry 0 function because it's bold. If you wanted to view any of the other functions, for example main, just double click on it and then it will load the main function in the disassembly window. And then at the bottom here, you can see there are a few tabs. We have the dashboard tab. The dashboard tab shows the overview of the information for this binary file, and the format is portable executable, which is a Windows exe file, and is 32-bit program, P32. And then you can also see over here the hashes generated, and below here are the analysis information. 49 functions have been detected, 356 cross-references has been detected, 271 calls made. These are calls made on those functions, and 335 strings has been detected. The 53 symbols refer to the function names, and then imports are those referring to the external DLL file. So these are all the imported functions, 53 of them. And then the second tab shows you the strings. So these are all the strings which has been detected by Cutter. So these strings are embedded inside the binary file. Then the next tab is called the imports. So these imports here are those external functions, and you can see here kernel 32 DLL. This kernel 32 is coming from the operating system itself. And this one, MSV CRT, is what I described here. These are the external Microsoft Visual C runtime libraries. Next will be the search. So here you can search for code as well as strings, hex strings, and 32-bit values and so on. Next is the disassembly view, which is the main one. And then you have the graph view. Click on the graph view to see the graph view. So the graph view is a graphical representation for what you see in the disassembly. In the disassembly view, you see the linear view for the assembly code. And then in the graph view, you see the graphical view. So you can zoom in and out by holding down the control button and then scrolling on the wheel of your mouse. You scroll up on the wheel of the mouse to zoom in, and you scroll down on the wheel of the mouse to zoom out. And then if you want to pan, you just left click, drag and pull to pan left and right. And then next at the bottom is, or the tab is called the hex dump. So the hex dump shows the memory of the disassembly. So this is what you see. Whatever you have in your disassembly view is being represented here in the memory view. So these are all hexadecimal notation, and on the right column is your ASCII representation. Sometimes if you scroll, you can see some strings as well. Presently you see jump characters because these are all the ASCII representations of the opcodes. Opcodes are the assembly language bytes. So over here you will see each one of these can be represented as an opcode. and that's what you are seeing when you look at the hex dump here, all this. So opcodes are the machine language. Next one will be your decompiler view. So you click on this, and decompiler view can be either using the Ghidra decompiler. Over here you can select Ghidra or JSDEC. So you can choose your decompiler here. So this is the decompile view for this assembly. This is in assembly language, and then here is your decompile view. So this is trying to mimic as close as possible to a C language syntax. And I must warn you that this is not perfect. Sometimes this could be even wrong or mislabeled. So at the moment, at the time of recording, we are not able to rename these variables here from the decompiler view. So these variables are given by Cutter to represent what it's trying to make sense of when it tries to decompile it. If you don't see any of these tabs at the bottom here, you can go to either go to view and then reset to default layout. So when you reset to default layout, all the missing tabs will reappear and show. Another way is to go to Windows and then go to Info, and then here you can add any extra tabs if you want. For example, if you want the call graph or global call graph, you can click on this. So when you click call graph, it will add another tab down at the bottom, call graph. So whatever is being shown in the disassembly here will be depicted in the call graph. So for example, over here you will see disassembly view, and this is the main function. If you double click this, it takes you to the main function. So the main function here is depicted in the call graph here. So the call graph is like a very high level overview of what other functions is being called by main. So you can see from here, main will call this function system, putString function, printf function, and then scanf function, string compare, and putchar function. So if you go and look at your disassembly view and scroll down, you can see the corresponding call here. For example, you can see here scanf function, printf functions over here. Then here you can see scanf function, and here you can see string compare functions. All these are C functions, and here is a putchar function. So the call graph is very useful for a high level overview of what other functions are called from within main function. And then you can go back to Windows and add any more under info. You can add any more other tabs that you want. For example, global call graph. So global call graph will show you the highest level view for the entire exe file. So here you have the entry point 0, which is actually here, entry point 0, and then entry point 0 will call your main function here. So this is your main entry point. This one is not the entry point for the executable. This one is like the pre-existing task that needs to be done before the main entry point can be loaded. So you can see from main functions here, you click on main, you will see it will bold the arrows, and from here main function, you notice that it also calls these other functions, and then from this function you click on this, it will bold the arrows below this, and from here you will call these other functions. So this is very useful to trace the order of the call of the functions. So that's how you can add or remove these additional tabs at the bottom. If you don't want this tabs at the bottom, you just can disable it from here, info, and just disable by clicking this button. So I'm just going to reset to default layout again, and it goes back to the original default setting. And then on top here you see a tab. The blue colored bands are where the code is found. So you can see here, this assembly view, this is where you can find code. Code are those instructions. If you click on the green, you will see 0 bytes. Add byte exal is actually 0 bytes, null bytes. They are not actually instructions at all, but they are showing up here misleading. It is misleading, thinking that it is actually add bytes. No, it's actually not. It's actually null bytes, all zeros. So, and then the red one here is the you can drag the red line here to go to any part of the exe file. So if let's say you are in a location out here, you go to this assembly, you will see nothing, right? And then you will go to graph, you also won't see anything because you are not in the function. Before the graph view can show any graphical view, you need to be inside a function. So for example, you have to click on any of this function. Then the graph view will be activated. If you're outside a function, for example, if you're here or anywhere where you're not in a function, let's say you're here, the graph view will not show because you are not inside a function. You must be inside a function by clicking this, then the graph view will be activated like that. When you want to view a graph view, make sure you must be in a function first by clicking the function, any of this function, then only click the graph view, otherwise you will see nothing here. You also have on top here the file menu where you can set the mode, write mode or read only mode. And then you can also save project. If you want to save any changes you made here or any analysis you have done, any comments you have added, or any renaming of the symbols that you have done, you can always save those by clicking File, Save Project. So when you click Save Project, it will ask you for a name. It ends with .rzdb, presumably resin database. So if you click Save, then it will save inside the folder for this track me. You can see here. And then the other thing you can do is over here, preferences, under edit preferences. If you click on this, you can go to appearance and you can change the interface. Presently is native and the color theme is cutter. If you want it to be a different theme, you can change to dark theme and automatically it will show you the dark theme at the back like that. And if you're okay with this, just click OK like that. You can change the color theme for the dark theme as well over here if you want. For example, basic looks like this, bold looks like this, and so on. And you can go to midnight. There's another dark theme here called midnight. Midnight. So midnight is even more darker than the previous one, as you can see. So this is your personal preference. However you prefer to have your cutter user interface set up. Alright, so if you like the dark theme, if you like the midnight theme and you're okay with this color, then click OK. And then next one will be here you can reset default layout, which I already showed you just now. You can notice here there is over here you have for every one of this you can detach it. So for those of you who have multiple screens, multiple displays, you can put this in the second monitor. And then you can keep on detaching any of these and pulling out to the side. If you want to redock it back, all you need to do is go to View and then reset to default layout. And then everything will be docked back inside again to the default view. Now here, when you are in midnight mode, this undock button shows up as a diamond shape. But if you go back to preference and change this to the native view, and click OK, the undock button shows up as the default undock button, like this, as you can see. See that? So the different views have different undock button, like that. Okay, so now I'm going to reset it back to the default view, reset the default layout. And then under Windows, you have your, you can add additional decompilers windows down here by clicking on this, like that. So now you have one decompiler, two decompiler. Alright, I'm going to close it. And then other things you can add are all these additional disassembly window, and info is I already explained. Debug is when you are doing debugging. When you are trying to run this as a debugger, then you'll be using this debug menu. So we'll be doing that later in the course. This debug here. You can set breakpoints as well. We'll be doing that later in the course as well. Then console, when you click on it, you will open a console at the bottom here. Okay, so that's for now. Let's go to menu, to main function. So if you want to insert a command, let's say at the back of this one, or maybe at the back here, you can press the shortcut key semicolon to open a command, and then type this is a command. Click OK, and it will show here. So the shortcut key is semicolon to open a command. The other way to insert commands is to right click here and then add command. So right click, add command, another command. You can type another command here and then click OK. So that is how you add commands. The next one is debug. So debug we'll be doing later in the course. This is when you are trying to use the debugger for dynamic analysis. Finally, we have help here, which shows you more information about this version. And then you can report an issue, and there's also documentation. When you click on documentation, it will go to the Cutter website and open the user docs. And here you can get more help, more information about how to use Cutter. Down here, let's say you are in any of the functions in the graph view, and let's say the program is huge. So sometimes when you scroll up and down or you drag and move around, you may get lost. So in order to know where you are, you can go to Windows here and then click on Graph Overview. So when you click on Graph Overview, watch what happens at the bottom left hand corner. So a very nifty little mini window opens up to show you where you are. So when you move around, this thing will help you to navigate where you are inside the graph view. So it's quite handy if it's a huge program with many blocks of code in here. So if you don't need it, you can just close it like this. If you need it, you just go to Windows and click Graph Overview. Okay, so with that, we will conclude this video for now. Thank you for watching. I'll see you in the next one. Hello and welcome back. In this video we are going to do static analysis. Static analysis is where you do not execute the executable. Instead you analyze the disassembly or the decompile view and view it to understand what is happening. So let's fire up our cutter, and then you will see that the history list is here containing the previous crackme that you opened. So just select it and open it. Here you don't have to write, you don't have to open it in write mode because we are not going to patch the file. We are just doing static analysis. And then make sure the analysis checkbox is checked and click on the OK button. So now immediately you will see the entry point 0 here, but as you have seen, the main entry point is the main function. So double click on the main function here, and that will take you to the main function. So immediately you can see the disassembly view. This is the linear view. If you wanted to see the graphical view, you can click on the graph tab here, and this will give you a graphical view. In C programming, the main function signature looks like this: integer main followed by argc and char argv. You can also look at the decompiler view here. This is what the C function looks like for main. Here you can change the decompiler to JSDEC or Ghidra. So let's look at the linear view first. So every function starts with a push EBP and ends with a return statement. Then over here you will see a few functions. You have your system, push string, and so on. Let us run the program first to see what it does. First thing it does is it prints the name, the string, hello, my name is Saptam. So this is obviously coming from this string here, my name is Saptam. Now before every call there is always the preparation for the call. For example, over here, this instruction here is to prepare for this function call. So here it is moving the string into a stack. ESP is a stack pointer, the stack. And then after it has moved this string to the stack, it will call pushString. So pushString is a C function for outputting some messages to the console. So you can open your browser and search for pushString in C, and you will get your explanation here. So pushString in C writes a string to standard out. Standard out is your console, your output. So in this case, this is called standard out. So that is what pushString does. So pushString accepts a parameter, a string, and then prints it out to the screen. So here is a copy. Here's an example of pushString. So in this case here, str1 is your string. So here you're printing the string out like this. So over here, the string that it wants to print out is hello, my name is Saptam. You can double click on this here. It will take you to your location in memory where the string is found. Here, hello, my name is Saptam. You can also look at the hexdump. Hexdump is a raw output in the memory, and you can see here the blinking cursor, and here is a corresponding string in ASCII. Hello, my name is Saptam. Let's go back by clicking the back button. Click the disassembly tab followed by the back button to go back. So this is what it does. It prints out this thing. Then after that you're supposed to print another string. to open this program, you have to enter my date of birth. So where is this coming from? It is coming here, from this second function call, put string. This time, it passes this string to the function. So you want to look at this string, you double click on this. Here you can see it. To open this program, you have to enter my date of birth. Alternatively, you can also go to hex dump and look at the blinking cursor. Here it is. To open this program, you have to enter my date of birth. Let's go back to your disassembly. So after that, it prints out this string to the screen. Then next thing is going to call is this function, printf function. So printf function is like put string function. It accepts a format specifier and the string is supposed to print. So let's take a look at the internet on what is this printf function. So just type printf in C, and then here you can go to the reference. So printf sends formatted output to standard out. So the formatted output is specified here. And if you scroll down, I believe you can see an example. Here you go, printf. So this is the format specifier to output the format that you want to see in the string. So when this printf runs, you will print this string, and when it comes to this format specifier, it will substitute the variable inside here and here, this variable in here. So that is the meaning of formatted output. So it is using printf here, and just as I've explained above, just before any call, the lines just above it are the preparatory instructions to get it ready for the call. So in this case here, it is moving this string into memory, into the stack, getting ready for printf to use it. So what string is this? You can see here the hint, enter date of birth. So double click on it, you can see the string here, enter date of birth in this format, 00/00/00, and that corresponds to this. So this is where this is coming from. This string is coming from here. Let's go back to the disassembly view, back button. So after it prints that message out, it's going to get ready for the next function, which is called scanf. So scanf is going to input. So now you can see at this point, it is waiting for the user to type in the date of birth. So scanf is going to read whatever the user types here. So you want to know what is scanf, you can go and search the internet. So over here, just type scanf in C, and here you can go and look at the description for scanf. The scanf function reads formatted input from standard in. So formatted input. And scroll down, you can see some examples. So over here it reads string format from string 1. So this is called formatted input, like this. So whatever it reads, it will be stored in your string here. So that's the meaning of scanf, is reading the input. So it's waiting for you to type something. So whatever you type here should be in this format. The month, the day, slash, followed by the second one should be the month. That means it should be, let's say, 02. Then third one should probably be the year. So the year could be 1933. So when you press enter, it's going to store your whatever you type in here into one of these variables, either S1 or S2. This one is a string format, 4044B, so I don't think this is the one. So you double click on that and go to hex you can see that here 25 is percentage, 73 is S. So percentage S is a string format. String format. Okay. So in C programming, string format will be, if you go to decompiler view, if you go back to this assembler, go back to the main function and go to decompiler view, you can see scanf over here. See that? So it's going to, this is a string format, and this one will be a variable which receives whatever you type. So this string format is percentage S. So let's go back to your disassembly view. So this is percentage S, and then there will be another parameter at the back, but it's not shown here. The second parameter at the back will be your will be the variable where you save your input into. Take a look at this, your variable. Alright. Okay, so let's go back to your disassembly view. So your whatever the user types in will be stored in one of these variables, S1 or S2. Remember, the lines just before a function call are the preparatory instructions. So these are preparing for this call. So because this call needs to use these variables. So in this case here, it makes use of this and either S1 or S2. We're not sure which one. That means S1 or S2 could contain the input from the user. Let's move on. So after it has read the input from the user and stored it in either S1 or S2, it will go on to the next one here. The next call is over here, string compare. So string compare, this is the function signature for string compare. It compares two strings, S1 and S2. So let's take a look at the documentation for string compare. strcmp in C. So string compare compares two strings character by character. If the strings are equal, the function returns 0. So it returns something. That's why there's the integer in front here in the function signature. So it's going to return 0 if its string is the same. Otherwise, it will return other than 0. So you can see an example of the usage here. String compare. It compares string 1 and string 2 and return an integer to the it returns an integer. Just if this result in the variable is 0, that means string 1 is equal to string 2. As you can see from here, the second call to string compare returns 0 when you print out. So string 1 is equal to string 3. String 1 is ABCD, string 3 is ABCD, so string compare will return 0. Okay, so that's how string compare works. It returns something. So normally the return value is stored in EAX register. That is why after this call you are testing whether the EAX register is 0. If it is 0, that means the strings are equal. That means string 1 and string 2 is equal. Okay, so string 1 or string 2, one of it is the input from the user, the other one is the actual password. So which one is the input from the user and which one is the actual password? Now we know from here, these lines here, it is preparing for the string compare function. And then from here, we can see it's using two variables, S1 and S2. And on top here, we can see it is constructing a string. So it's constructing a string which starts with 07/1 and then 0/97. That means it is constructing this string. Let me open a notepad. It is constructing this string 07 1, which comes from this instruction. Then it continues with 0/97. 0/97. Finally, it puts a null terminator at the back. Now in C programming, a null terminator is a way to tell a program the end of the string. It's like a full stop. So at the back is a null terminator. In C programming, a null terminator is denoted by \0. This is an invisible character. So we know that he's creating a string here, and this looks like the password, the date of birth. So after it has constructed the string, it moves the string to EX. LEA means load effective address. That means it's getting the address of the string. The string is actually the whole thing, not just 1CH. But 1CH is the start of the string, and the end of the string is at 24. This is memory offsets. So at memory offset 1C, H here refers to the hexadecimal. So 1C means memory offset 1C for the var. This is just a name, by the way, and telling you the offsets, the relative offsets from the start of this variable. And this is the actual address. So this is the actual address where you will start to store your password. And this address 0x is 0x means hexadecimal, and then 312F3730 is a memory address. So now it moves this whole string into EX, and then it moves it into S2. That means S2 is the actual password. Therefore, we can deduce that S1 is what the user input. So scanf will store the user input in S1. And then S2 will store the actual password. And then when it comes to string compare, it compares S1 and S2. It compares what the user entered in S1 with the actual password, which is in S2. And if they are the same, the test EX here will be 0. So test EX, EX means it is testing whether EAX is 0. If EAX is not 0, then it will jump to this location and print this message, access denied. So put string here will print access denied. But if your EAX is 0, then it will not jump. Instead, it will move forward, and then it will come to this message here. Put string, access granted. You come to this message here, access granted. So you can test our hypothesis. This is the password, so we are going to put that password inside and see whether it works. So let's put the correct password, 07/10/97, hit enter, access granted, and then welcome. So this access granted, where is it coming from? It's coming from this string, access granted. So you double click on this, it will show you the string access granted. Let's go back. Following that, you will pause. So you will call the system to pause. That means you can see now it is paused. Press any key to continue. So this system call is to pause the program, waiting for you to press something to exit. Okay, so this is how you can do static analysis from the linear view. You can also do static analysis from the graph view. Click on graph. Make sure you go to your function main first, and then go to graph view. So here is exactly the same. You can see over here it prints hello, my name is Saptam, and then it puts string, you have to enter my date of birth, and then it prints F here, enter date of birth. So all this is exactly the same as what we have seen. And then here is just to read the input from the user by using scanf and storing it in S1 as you have seen earlier. and here it creates the actual password out of these 3 instructions, and then move it to S2, and here it compares whether S1 is equal to S2, and it tests if the string compare is that compares S1 and S2 finds that both are the same, then it will return 0 to EX, and here is where we test EX, and if EX is not equal to 0, it will jump here, and then it will show you the bad message, access denied. But if EX is 0, then it will jump over here and shows you access granted, and after that it will call the system function to pause the program and then leave. Okay, so this is how it works. You can also look at the decompiler view, more or less doing the same thing. Over here, it prints hello, my name is Saptam to the screen. Then it puts string open this program. You have to enter my date of birth. Then it uses printf to print the date of birth prompt. Then it will read whatever the user type and store it in this location. This is S1 as you have seen earlier. So this AU stack is S1. And then over here it will compare. Over here it will create the actual password. These 3 instructions is referring to these 3 instructions here. So it is creating the password, these 3 instructions. You store the password in stack 36, and this is your S2. So you compare S1 with S2 using string compare. If the strings are equal, it returns 0. So here is where it's comparing whether it is 0. If it is 0, you print the message access granted, and then if it's not 0, you will go to the else statement and print access denied. Then you will call the pause. You will call the system to pause the program. So this is how you can do static analysis to solve this crack me. Thank you for watching. In the next lesson, I will show you how to do dynamic analysis using the debugger. See you then. Hello and welcome. In this video, we are going to do dynamic analysis. That means we are going to execute and run the program, and then we are going to analyze it using the debugger. So Cutter has the built-in debugger. Let's open Cutter now. Now before you do anything, make sure you make a copy of your crack me. In case you make mistakes, you will have a backup. So let's open the crack me now, and make sure that you click on load in write mode, and analysis must be checked. Click OK. So now double click on main to go there, and before we execute it, we are going to put a breakpoint. So select the push EBP of the main function, right click on it, and click and scroll down to breakpoint and select add breakpoint. The shortcut key is F2. So you see it's red now. Push EBP has got a breakpoint set. If you go to the graph view, you will see the same thing. Let's go back to this assembly. So now we can click on the start debug button here. So just click OK. Here also just click OK. And so click on continue until it hits our first breakpoint. Click continue again. And now let's see. Click continue one more time. And now we are at the first breakpoint, push EBP. You can see all the breakpoints by going to debug, by going to Windows, debug, and then breakpoints. So under breakpoints, you can see here breakpoints, whatever breakpoints you have. Now I have put the hex dump underneath here and set it to unsync. if you click on this, right click on this, you can set it to sync or unsync. You should set it to unsync because every time you want to view the hex dump, if you are synced, it will always change the disassembly view to follow the hex dump, and you don't want that. So you must set it to unsync. Right click on this to toggle to unsync. So once you set to unsync, you'll be able to view the hex dump without altering the disassembly view. So if your hex dump is not at the bottom here, you can pull it to the bottom. For example, if your hex dump is not here, and you can, let's say your original default view is like this. Your hex dump is in a separate tab. So in order to put the hex dump below here, you can just go to hex dump and click this to undock it. So your hex dump is now undocked. You can pull it to the bottom and then release. So now you'll be at the bottom. So let's go back to disassembly view. So now we are at the breakpoint push EBP. We can step over it by clicking this. You have step over, step into, and step out. Step over means you just want to go through the lines, each instruction line by line, without entering any of the function calls. So let us now step over by clicking on this. So now you're at the second instruction, move ESP to EBP. Step over again, and now you're here. Continue to step over. Step over. So now you are going to make this function call using these parameters for this function. We are not interested in that, so we just step over. If you want to see what's happening inside, you can click step into, but it's not necessary. So we are stepping over. Again, it's going to push these parameters to the stack to get it ready for this system function. So let's step over. Step over. This is probably to set the output to become green color. Now it's going to push this string to the stack to get it ready to call the put string function down here. So it's going to push this to the stack 4040C. You can see it here later. Let's step over, and you can see 4040C contains this string, hello, my name is Subthumb. So now the stack will contain the parameters for the next function call. So in this case, the next function call is putString. So putString is going to make use of this string. So let's step over, and now you should be able to see something. Hello, my name is Subthumb. So this is coming from the putString function here. Next is going to push this string to the stack at 404068. So watch what happens to the stack. Step over, and you see it here. You can so this string is now in the stack, you're ready for the next call, putString. You want to see this in a memory, you can right click on this, show in hex dump, and you can see here. To open this program, you have to enter my date of birth. Okay, so let's go back. So you notice my hex dump is not unsynced. That's why my disassembly also changed. Alright, that's the reason why I advise you to right click on this, set it to unsync, so that your assembly will not change. Let's go back to main. So now you're here. So when we step over this, it's going to output this string. So let's step over, and you go back here, you can see this. Alright, so this string is coming from this function call. putString. Next is going to push this string to the stack at 4040A2. So let's take a look at the stack. And now you can see 4040A2. So now you want to see this in the memory. You right click, show in hex dump unsync. Can you see that? Enter the date of birth 0000 and so on. So notice the disassembly did not change because we unsync the hex dump. So now it's going to print this string to the output. So let's tap over this. So now take a look at the output and you will see this string. So this string is coming from printf. Next is going to go to the scanf. So let us step over. Okay, so it's pushing all these parameters for scanf. And then you can see 40BB. So if you want to know what's 40BB, you can right click on this, show in hex dump unsync, and you can see here 4BB is this percentage symbol, and beside it is S. So percentage S is your format specifier for scanf. And then now we're going to step over scanf. Alright, so now we go back here. You're supposed to enter the date of birth. So I'm going to type 01//02/03 and hit enter. Once I hit enter, scanf will have saved my date of birth that I entered into the stack. So you want to know which one contains the date of birth, you can analyze it by right clicking, show in hex dump unsync, and you can see this is the location in memory where where my date of birth that I entered has been stored, 010203. So now is going to go next to the next function call, which is string compare. So string compare has got two parameters, so all this instruction is to prepare to load these two parameters to the stack. So let's tap over them. So let us tap over. So it is about to call string compare. So at this point in time, this S1 and S2 is already on the stack. So one of it is the password, the actual correct date of birth, and the other one is the date of birth that we entered. So which one is the correct one? So we can just go through each one of these and look at it in the hex dump and we will see it. Starting with this, right click, show in hex dump unsync, and you see here 010203. So this is not the correct date of birth, this is the one which we entered. Now go to the next one, right click, show in hex dump, and immediately you will see 07/10/97. So this is the correct date of birth. So at this point in time, we have already managed to fish out the key, the correct password, the correct date of birth, just by doing dynamic analysis. So we know that this is the correct one because in the previous lesson we already tried this using static analysis. Okay, so now we are going to step over the call. So once you call string compare, is going to compare the two strings. If the two strings are equal, then it will return 0 and store in EX. If the two strings are not equal, then it will return other than 0. So if you look at EX now, you will see that it is not 0, it is -1. Now when you see 0x followed by all f's like this, it means -1. This is a notation, one's complement notation for showing negative numbers using this computer binary number systems. So all f is in hexadecimal means all ones in binary. So all ones in binary means -1. So over here now we know that this test is going to fail because test EX is testing whether EX is 0. Since EX is not 0, this test is going to fail, therefore jump not equal will be true. So let's step to that now. So jump not equal is going to be true, so it's going to jump down here. So let's step over and see jump. So it jumps down here and it's going to push this bad message to the stack at this address 404ODA. So let's take a look at the stack. Step over it and you see at 404ODA. If you right click on this, show in hex dump, unsync, you will see there, access denied. Alright, so it's going to push that to the stack, and now it's going to call the push string to show the bad message. So let's step over that. Click on step over this push string, and you should see the bad message, access denied. Okay, so now we step over again, and now it's going to call the system. It has just pushed this value to the stack, pause. So if you go here, right click, show in hex dump, you should be able to see the pause parameter. This parameter is going to be passed to this system function call. So let's step over that function system call now, and you will see it has paused, waiting for it to type something. So now we know that the correct password is, let's open Notepad and type in the correct password. The correct date of birth is 07 slash 10 slash 97. Alright, 071097. So now we are going to stop this and restart it, but this time we are going to enter the correct password. So we use the same breakpoint, click OK, and let it run to our breakpoint. So we're now at our breakpoint. Let us step over, continue to step over until we reach the scanf function. Okay, so step over the scanf function and now type the correct password. So our correct password is this one, 071097. 07 slash 10 slash 97, hit enter. Okay, so now it has stored our password in one of these parameters, show in hex dump. You can see 071097. This is what we just entered. So we step over now until we come to the string compare. So now string compare is comparing S1 and S2. Let's take a look at the parameters. Okay, this is 071097. Look at the other parameter, 071097. Same. That means this time string compare is going to be returning 0 to EX. So let's step over, and now we see EX. Indeed, it is 0. So because it is 0, jump not equal is going to be false. So it is not going to jump, it is going to go straight. Let's step over. See that? It went straight. And then now it's going to push this string to the stack at this address 4040BE. Let's take a look. Step over. Right click, show in hex dump, and you can see the string has been pushed to the stack at this memory location, access granted. So now it's going to use that to put string to the output. So let's type over put string, and then you will see access granted. After that, it's going to push another string to the stack. So let's step over. So let's go to this, the stack, right click, show in hex dump, and you can see here the message welcome. So it's going to call push string to print welcome to the output. So let's step over that and let's go to the output, and you will see welcome. Then we step over again. Now it's going to put char. Put char is just a blank character output to the string. We are not interested in that. And now it's going to do the same thing for the system to pause. So let's step over, and you can see the pause has been sent to here. Pause is there, and it's going to call system to pause it. So when we step over it, it will pause, waiting for you to type something to continue. Okay, so now we have solved the thing using the correct key, the correct date of birth. So this is how you can do dynamic analysis to solve the crack me. In the next video, I'm going to show you how to patch the binary. So that's all for this one. Thank you for watching. Hello and welcome back. In this video, I'm going to show you how to patch the binary file so that no matter what password or whatever date of birth that you enter, it will always be correct. So let's try it now. So let's open Cutter, open the crack me. Here, make sure you check on this checkbox, load in write mode, because we are going to patch the binary, we are going to modify the binary. So the word patching means to modify the binary. Make sure analysis checkbox is checked and then click on OK. And then go to the main function by double clicking it here. So now we are going to set a breakpoint. If you go to your breakpoints tab at the bottom here, you can see if there are any breakpoints being set. You can also delete all breakpoints by clicking the delete all breakpoints button, or you can delete a specific breakpoint by selecting it and then clicking this button here. So let's do the graph mode this time. Earlier on we tried the disassembly, so now we try the graph mode. So we are going to set a breakpoint here by right clicking the push EBP, which marks the start of the function, and then scrolling down looking for breakpoint and clicking add breakpoint. So now the breakpoint is set. As you can see, it is highlighted in red, and the important jump is here. So in the previous few lessons, we've already seen how this thing works. So how this thing works is that when it comes to this part here, it will do a string compare using the string compare function that comes from this library. The string compare function will compare the real date of birth or the real password or real key with the one which you enter. If they are equal, then it will return 0, which will be stored in the register EAX. And then over here, called jump not equal. Jump not equal will then check whether or not this EAX test was true or false. If EAX is 0, then jump not equal will be false. It will then go to the left part here. However, if EAX is other than 0, then jump not equal will be true, and it will go to the right hand side to show you the access denied message. So what we want is to reverse this jump so that it will always go to the left. So any wrong key that we enter, any wrong password that we enter, it will go to the left. So to do that, all we need to do is to reverse this jump. But before we do the reversing of the jump, just try to run this now, and I'll give you a sense of how it works. So let's click on the Start Debug button here. Click OK. Click OK again. And then now, click Run until it hits our breakpoint. The graph view is empty because it hasn't entered our main function yet. So click on pressing this. We are now in disassembly view. And then click Continue. And now the screen has popped up. Click Run again. It hasn't hit our breakpoint yet. Click Run again. And now it has hit our breakpoint over here. Now let's go to the graph view, and it's over here. It's hit our breakpoint here. So we step over it by clicking this button, and we are now here. We keep on stepping over and over and over until we get to the scanf function. So now we are at the scanf function. Let's step over it. So now we have stepped over it. If we head back to the output, we will see that it has paused here to wait for us to type in something. So let us type in a wrong date of birth, 01/02/03, and hit enter. So after we hit enter, the scanf would have saved the date of birth which we entered into the parameters, one of the parameters here, and we have seen it is actually this parameter. If you right click show in hexdump unsync, make sure your hexdump is unsynced by right clicking and setting to unsync. Otherwise, when you go to hexdump, it will also move your disassembly or graphical view. We don't want that. So right click on this and show in hexdump, and you can see here is the blinking cursor, and on the right you can see the square box here which marks the start of the string which we typed in. So this is what we typed in. So now let's continue stepping over until we come to the string compare. So let's step over. So now it is at the string compare function which it is going to execute next. So it has already got ready these two parameters in the stack here, and both of them have got, one of it has got the real correct key or the date of birth, and the other one has got the wrong one which we entered. So as we have seen, string compare will compare the two strings to see if they are equal. If they are equal, it will then return the value 0, which should be stored in the register EAX. So let's see now. Let's step over this and see what happens. So we have stepped over this now, and now we can examine the register EAX. So now let's examine the register and see what is stored in EAX. So if we go to the register, we see that EAX stores -1. So -1 is not 0. So this test will fail. So over here, it will perform the JNE. JNE means jump not equal. So because EAX is not equal to 0, so JNE will be true. So it will jump to this address on the right, which is 401667, which is here, 401667. So it will jump to here. So because we don't want it to jump here, we need to reverse this jump. So in order to reverse this jump, we have to right click and then edit, reverse the jump. Okay, so before we did that, we can right click and put a comment there and type in reverse this jump, and click OK. So this is a note to ourselves saying that we are supposed to reverse this jump. So now let's try to reverse this jump by right clicking this and then coming down to edit here. So in the edit menu that pops up, scroll down to the last one and reverse the jump. So what is the opposite of JNE? What is the opposite of jump not equal? Let's take a look. The opposite of JNE is JE, which is jump equal. So this has the effect of reversing the logic. So now if you step over it, it was supposed to go to the left, because it will go to the left because EAX is not equal to 0. Okay, so let's step over it. JE means jump to the right only when EAX is 0, but now EAX is -1, therefore it will jump to the left. So let's step over and see this whether it works. So we step over now, step over, and you see now it goes to the left and it's going to load the good message to the stack and then put it out to the display. So let's see that happening. We just keep on stepping, and now we come back and see the output. We have managed to reverse the jump. So our theory works. So that means this is correct. Okay, so in order to make this permanent, we have to restart it again. So we are going to stop this now, and then now we are going to make sure that our file is in write mode. So we go to File, we go to Set Mode, change to write mode. Okay, you have to set to write mode, otherwise the whatever changes you make will not be saved. So now it is in write mode, and you can see our useful command which we wrote while we were in debugging mode is still there. So now we know we're supposed to reverse the jump. So go ahead and reverse the jump now while it is outside of debugging mode. While you were in debugging mode, whatever changes you made is only temporary. You have to exit the debugging mode in order to make the changes permanent. So now we are going to make it permanent. So that's why we had to write this command to remind ourselves that we are supposed to reverse this jump. So now to make this permanent, just go and right click this and repeat the same thing, edit, and then go to here, click on reverse jump. That's it. That's it. So now you can quit this program, or you can save a copy if you want, save a project, so that you have all the commands being preserved for you. So you can save the project now under this same folder with the extension RZDB and click save. And now you can quit this, click save, and now you can see there's a new file, the RZDB. DB is a database for this project. So now we can test our patch file. So we double click this and we can enter any wrong password, any wrong date of birth, and see what happens. So we type 01, 02, 03 and hit enter, and you see access granted, welcome. So we have successfully patched this. Okay, so before you do this, you already made a copy of the binary, so that in case there's a mistake, you still can fall back on the backup copy. So that is why it is important to make a backup copy in case you made a mistake, because whatever patches you made is irreversible. Okay, so that's it. So this is how you can patch a binary. So that's all for this video. Thank you for watching. Hello and welcome back. In this video, I'm going to show you another way to patch the binary. This time we are going to use NOPs, no ops, also known as no operations. So previously we already have a version where we reverse the jump, and this is the one. So let us rename this. So we rename this as version 1, V1 is for version 1. And now we'll make another fresh copy from our backup. So we take this, copy, paste it here, and rename this back to the original. So now we have a fresh copy which is not yet patched. So now we are going to open Cutter and make use of this fresh copy. So you can open it direct, but if you want to preserve, you want to reload back the commands which you entered in the previous project, then instead of loading this directly, you can load it indirectly by clicking the project and then select this project file, RZDB. So go to the desktop or wherever you saved your files, click on RZDB. So RZDB will open and will also load the CrackMe directly. So click open. Then double click on the main function and you will see that your command has been preserved. So this was the command you entered in the previous project, where we reversed this jump by converting this from JNE to JE. So now in this project we are going to use another method. Now notice here that when it comes to this line here, if you had entered a wrong password, it's going to jump down here to show the bad message. So instead of allowing it to jump here, you can replace this instruction with NOP. NOP means no operation. So let me show you what I mean by NOP. So if you head to your Google Chrome and search for NOP, you will find the explanation here. In computer science, a NOP, pronounced as no op for no operation, is a machine language instruction and is assembly language mnemonic, programming language statement, or computer protocol command that does nothing. That's it. So that's why you use NOP. So NOP for our Intel CPU is denoted with the hexadecimal 90. So 90 is 1 byte. This is 2 bytes. And this one I think is 6 bytes. So every 2 digit is considered 1 byte. Okay, so you can count. So since there are 2 digits here, it means it's 1 byte. So 90. So over here, if we don't want our jump to take place, we can replace it with a 2 90s. Why? Because JNE takes up 2 bytes. I will show you later how I know that. So at the moment, we are going to go to our main and we are going to set a breakpoint here so that we will walk through, step over and see how it works. So let's set a breakpoint, right click and then go to breakpoint, click on add breakpoint and then click on run. Click OK, click OK again. Now keep on pressing this button continue until it hits our breakpoint. Again, now it has hit our breakpoint and we keep stepping over it until we come to our scanf function. So now we are at scanf, step over it. This is the scanf function, we step over it. So now it has stepped over. Now we are supposed to enter a password. So we enter the wrong one, 01/02/03, hit enter. And now it has saved our date of birth inside the parameter in a stack. So you can right click on this, make sure your hexdump is unsynced and then show in hexdump, confirm it. And you can see over here 01/02/03. Now we continue to step over until we come to okay. So now over here it has compared the string, and if you look at the EAX here, you can see it's -1, meaning that the strings are not equal, therefore it's going to come down here and test. If the test is EAX is not equal to 0, it will come here and jump. It will jump and it will load the bad message. So we don't want it to jump, we want it to go straight. So if we want it to go straight, what should we do? We should nullify this instruction by replacing it with no operation. So the effect of this is to make it go straight. So if we were to look at the graph over here, going straight means in this case it will be going to the left. So that is why when you're trying to do a no operation, it will be helpful to look at the linear view like this so that you will know what happens, what instruction comes after the jump. So after the jump instruction, there is all this instruction, the good instruction. If you had looked at the graph view, you will not know what comes after the jump. Is it this or is it this? So that's why you take a look at the linear view and you will know that after the jump, if the jump doesn't happen, it will go straight. So that's how we can know that we should put a no operation here. With a no operation, it will go straight, because a no operation literally removes this instruction and replaces it with NOP bytes. So NOP bytes are 90 and 90 again. So if you wanted to know how many bytes JNE takes, you can right click on this and click on edit. But before that, you need to click on file, set the mode to write mode, and then you right click on JNE, go to edit and click on edit instructions. Then you will see this instruction, below that there is a number 7526. 75 is 1 byte, 26 is another byte, so total 2 bytes. That means this instruction takes up 2 bytes. So this is the machine language, also known as the opcode for the assembly instruction. So now we know that this instruction takes up 2 bytes, so theoretically we should replace 2 NOPs in here. Alright, so you will see that happening. So we click cancel now. Now we are going to put a remark here to remind ourselves that we are supposed to no-op this. So right click on this, edit command, and then change the command to no-op this. Click OK. Now we try it. We right click on this instruction, and then we come down to edit and select no-op. And you will see it has replaced the jump instruction with 2 no-ops. So each no-op is 90, another 90 here. So if you look at the hex, you can see it as well. So if I were to right click and sync this hex now, you can see here there is 190 here, and then below that there's another 90. So this 90 is the first no-op, and the second 90 is the second no-op. Okay, so the size is still 2 bytes. So that's why it works. You cannot replace an instruction which is larger than 2 bytes, because if you did that, it will overwrite the instruction below this. So it will overwrite this and this and this, and that will render your program unable to run, because it will have corrupted all the instructions. That is why it is important to check that whatever new instruction that you are going to use to replace the ones that were already there should not be more than the size of the original bytes. So in this case, now we replace the no-op, it should go straight rather than jump down to this location to show the bad message. So let's see that happening. So let's step over now, and it has gone straight. Take a look. Jump, step over again, and if you go to the graph view, you can see the same thing. It has gone to the left, which means going straight. So now if you continue to run all the way, keep on stepping over and stepping over, you will see the good message here, access granted. So this is how you can use no operation to nullify the existing jumps. Okay, so now we have to make it permanent, so we stop the debugger and then go back to main, and then scroll down and look for our command. See this? No-op this. So this is where we are supposed to no-op. So now we'll no-op it. Make sure you are still, the mode is in right mode, correct? Right mode. So now we right click this, and then we go down to edit, select no-op instruction. Okay, reopen in right mode. Okay, fine. Now you have no-op the jump instruction. So now you can save your project and then close your cutter. Save again. Close this, and now you can test your new patched file. Double click and just enter any wrong date of birth, 01, 02, 03, and you should get access granted. So this is how you can use no operation to nullify the jump instruction, and how you can patch the binary file with no ops. Just close this here. So before you end it, just rename this as version 2. Right click, rename, and call this -v2. So that's it for this video. Thank you for watching. I'll see you in the next one. Hello and welcome back. In this video, I'm going to show you another method of patching in order to cause the program to show the good messages. This time we are going to deliberately set the EX register to 0. So in the previous lecture, I've already done V2, so let's create a fresh copy of the correct me by copying this pasting it here and rename it back to the original file name. Now we'll open our cutter program, go to the projects, load the project, and this project will load our fresh copy of the crackme file, and you scroll down, you will see our fresh copy here, and this was our first version where we know of this, so we can remove this comment. Just right click and edit it to delete the comment there. So this time we are going to try a different approach. We know that the string compare function will return 0 and save it in EAX if the strings S1 and S2 are equal. But if they are not equal, it will return -1 and store it in EAX. So why not we manually set the value of EAX to become 0. So how can we do that? So the strategy is to insert an instruction that will cause the EAX to become 0. So let me show you what I mean. How can we set EAX to become 0? We can use a technique called XOR EAX. XOR EAX will cause EAX to become 0. So assuming you have a value in EAX originally as 1, 2, 3, 4, 5, 6, 7, 8. So when you XOR EAX, what you're doing is doing an exclusive OR operation. So this, assuming EAX has got this value in binary notation, one value with another value, you are taking the first value, assuming this is the value on the left, you are XORing it with the value on the right. So the effect of this is, if you take 1 and you XOR with 1, what do you get? You get 0. So this will return you 0 for the first column. Same thing with the second column. So the meaning of XOR is that when you compare two bits, both bits must not be the same. That's the meaning of XOR. XOR means exclusive OR. Exclusive OR. So this is a logical operation. So either the first bit is 0. If the first bit is 0, then the second bit must not be 0. If the first bit is 1, the second bit must not be 1. So they must be both different. That is the meaning of exclusive OR. So in this case, since the first bit and the second bit is both 1, the result is 0. That means false. So XOR is actually testing whether the first bit and the second bit are different. If they are not different, then it's false. Same thing with the second column. XOR 1 with 1 is also 0. So in the end, what you will get is all zeros. That means you should get all zeros. Because when you come to this column, XOR 0 and 0 is also 0. Why? Because both are zeros. You cannot have both zeros. One must be a 1. So say that's why XOR 0 is 0 is also 0. So in the end, that's the effect of XORing EAX with itself. You get 0. So this is an instruction which can cause EAX to become 0. And it only uses 2 bytes. 2 bytes. The instruction takes up 2 bytes. Okay, so now you know this. Let's go and take a look at how we can use this inside our cutter. So where is the best place to XOR it? We can perform the XOR over here itself. We replace this call with XOR EAX. So let us test it first with a debugger to see if it works before we patch it. So you put a breakpoint here by right clicking this, add breakpoint, and now we can run. Click OK and OK again, and then click continue until we hit the breakpoint. Click continue again, and now we hit our breakpoint. So now let us step over until we come to this line here just before the string compare. Okay, so now we are going to hit the scanf. Once we step over scanf, we need to enter our date of birth. We set 01/02/03 as a wrong date of birth. Hit enter. So now we know for sure it's a wrong date of birth. So let's step over until we come to the line, just one line above string compare. So at this point in time, string compare is going to compare and is going to return a -1 inside EAX. We did that before in the past few lessons. So in order to prevent string compare from setting EAX become -1, what we want is we will manually set EAX to be 0. Okay, we can set it to 0. So what we do is we will right click on this and replace this instruction with XOR EAX, which is what we just saw over here. XOR EAX. But XOR EAX takes 2 bytes. Now, how many bytes do you think this instruction takes? Is it 2 bytes or more? Let's take a look. We right click on this, we do an edit instruction, but before that, we will have to set our mode to write mode. So go to set mode, write mode. So now we right click this instruction, and then we click on edit instruction, and we will see that this instruction is represented by this opcode. And this opcode has got 5 bytes. E8 is 1 byte, FF is 2 bytes, 0F is another byte, so 3 bytes, 4 bytes, 00 is another byte, and then the last 2 zeros is another byte. So you have 5 bytes, 1, 2, 3, 4, 5 bytes. So remember, our call to string compare function takes up 5 bytes. So let me write the notes here so that you can understand. If we were to replace this string compare call with XOR, we only need 2 bytes. So what will happen to the other 3 bytes? Let's take a look. So now we are going to replace our string compare function with XOR EAX. XOR EAX. And as you can see, XOR EAX takes only 2 bytes, just as we predicted. It takes 2 bytes. And then we will have another 3 bytes excess. So 3 bytes will become the next instruction. So let's see what I mean. So if you click OK now, watch what happens to this line. So you get XOR EAX, so this takes 2 bytes. You can confirm that again by right clicking it, edit instruction, and you can see it's 2 bytes. Now take a look. This new instruction came out of nowhere, and this instruction, let's take a look, edit instruction, takes up 3 bytes, and this is the remaining bytes that came from our previous instruction. You remember 0f0000 came from the previous instruction. So what cutter has done is, cutter has mistakenly interpreted these remaining 3 bytes as an instruction and put it in here. So this is actually a junk instruction. It's not really an instruction, but cutter tried to make sense of these 3 bytes and therefore replace these 3 bytes in a readable form as SLDT and so on. So what we need to do, we need to no-op these 3 bytes. Okay, so let me write the notes first. We need to no-op these 3 bytes. So we write a command here, right click, add command, no-op these 3 bytes. And then the previous one, we write a command also, add command, and we say we need to XOR EX this. So this will take 2 bytes. This was previously a call to string compare, so we only use 2 bytes. You see that? So XOR EX takes up 2 bytes, and then the remainder becomes here. So this should be wrong command. Let me edit that. This should be 3 bytes. Oh, this 3 bytes. Like that. Okay. So total 2 bytes here, 3 bytes here. So we need to no-op this. So let's do it now. Right click, edit, no-op instruction. So now we have 1, 2, 3 bytes. So 2 bytes from XOR EX and 3 bytes from this 3 no-op. So total 5 bytes. So originally we had 5 bytes from here. So now we have split this into 2 bytes for XOR, and then the remainder 3 bytes, we no-op them here. Alright, so this is very important because we have to make sure that any junk instruction is no-op. Otherwise, when it came over here and tried to perform the junk instruction, the program might crash. Okay, so that is done. So now let us step over this and see whether it works. So now we have manually forced EX to become 0. Let's see the register here when we step over it. Now presently EX is not 0, so let's step over this XOR and EX became 0. See that? And this no-op will just fall through, we just step over. Keep on going until the end, and then now we go and take a look. We have managed to bypass the jump, and by doing the manually setting EX to become 0, so it worked. Now there's one thing I need to caution you. Although the system works in this case, before we XOR this was a call to string compare, remember? And as you can remember, just before any call, the preceding lines are actually pushing or setting up data either in register or in the stack to make it ready for the call. So this actually has tainted the stack. The stack is corrupted actually with all this data. So strictly speaking, we should also no-op all these instructions. We should no-op all these instructions because all this instruction is to set up for the next call, which is string compare. But now the string compare is normal there. By right, we should also no-op all this. So if you were going to really do this in any other programs, you should no-op all this as well. But in here, I just leave it out because it has no effect on the program. But in other programs, if you were to leave this here, then it might cause some problems in the execution later. Alright, you should no-op this. Alright, the reason why this thing should be no-op is because if you don't know, other part of the program which requires the register or the stack might read the wrong values from the stack. Now if the call were there, the call would have taken care of the cleaning of the stack. But since the call did not take place, the call to string compare, we have already removed it, so the call could not clean the stack. Now in assembly programming, the call will always take care of the cleaning of the stack. So in this case, the call is not there. That is why, strictly speaking, you should clean the stack by setting no op up here. Okay, that's all. That's the only warning I like to tell you, to be careful about that. Alright, so now let us patch this file. So I'm going to stop this now. We already put our comments, so we know where to patch. So let's stop this debugger. And now we are going to patch. Go to main. And then we are going to set the file to become set mode, write mode. So let's go down and look for the comments which we have written. And we can see our comments. Here you go. This is our comment. XOR EX is 2 bytes. And then later on we have to no op as well. So let's do it now. So we right click this. And then we edit instruction. Click reopen in write mode. XOR EAX. EAX, click OK. Alright, so now we XOR this. We use 2 bytes, so the other 3 bytes we need to no op it. So right click, edit, no op instruction. So 2 bytes here, 3 bytes here, 5 bytes. So now we can just save this, and then we can quit the program since we have already patched the file. So let's quit it, save again. Okay, so now let's try our program. Just enter any wrong date of birth and it works. See that? So this is how we can modify the program to perform certain to prevent a certain jump by modifying the EX register to become 0 using the XOR EX instruction. Let us make a copy, rename this to become version 3. Rename this as -v3. So far we have done 3 different ways. So version 1 was to reverse the jump, version 2 is to no op the jump, version 3 is to XOR EX. So that's all for this video. Thank you for watching. Hello and welcome back. In this new section, we are going to get started with GUI Crack Me's. So go and download this GUI Crack Me from the resource section for this lecture. Unzip it and put it in your Crack Me's folder. The password to unzip it is crackinglessons.com. Inside it, you will find a Crack Me written by me. This Crack Me is available also from my website. So you go to my website, it is available over here under challenges. So over here are all the Crack Me's that you can download from my website. If you go to number 3 here, you will see the same Crack Me here, Crack Me 1. So this is a GUI Crack Me written in Visual Studio 2017 Win32 API. So the objective is to find the serial key and enter it in the text box. This is what it looks like. And then you can patch the file to always show the congrats message when the button check is clicked. You can download it here, or you can download from the resource section for Udemy. And this is the password to unzip it, crackinglessons.com. So after you download this, some of you might find that it is malware. You might, please don't upload to VirusTotal. So many people that uploaded to VirusTotal, in the end it became tagged as a malware. It is not malware, it is written by me, and it is not malware. So virus total will give you false positive. Even your Windows Defender will say it's malware, but those are false positive. Alright, so anyway, if you really want peace of mind, please remember to run this in your virtual machine. So this is my virtual machine here. I'm running this now. So if I double click on this is what it looks like. And then here it asks for the serial key. If you enter a wrong serial key and we click the check button, you will get a bad message, sorry, wrong serial key, try again. So now we are going to try to learn how to crack this software, this program, by using Cutter. So let's open Cutter now and take a look. So let's close this program. So select your GUI Crack Me 1 and open it. Make sure analysis is checked and then click OK. Alright, so this is you will see this is the graphical view, and then at the bottom we have this assembly view. And then if you scroll all the way down, you see all the functions that are detected. And then down here you have a main function as well. And then you can look at the main function. So this is what it looks like. Now when you ran the program earlier and you enter a wrong serial key, click check, it shows you this dialog, this message box. This message box has got this string. So one way of trying to solve this crime is to search for the string. Wrong serial key, try again. So we can search for it by going to the strings here. And then it lists all the strings that it has found. Look for wrong, and then you will find there's one hit. Wrong serial key, try again. So now you want to know where in the code this is being used. So you can right click and then select cross reference, show cross reference, and the shortcut key is X. So just click on this and it will show you where in the code this string is being used. So once you found it, you can just double click on this to go there directly in your graph view or disassembly. So let's double click, and here it shows you wrong serial key, try again. So let's analyze this. You can view it in a graph view also, but you need to define a function before you can view it in a graph view. So we do not know which of these functions this refers to. So we need to create our own function here. Look for the return statement. So the return marks the end of the previous function. And the first instruction after return is the start of the new function. So we can right click on here and define the function here. And then here we can call it myfunc. And then click OK. We put my in front so that we can distinguish it from the rest of the other functions. So click OK. Now you can scroll down, you see there is a myfunc here which you just declared. So once you declare a myfunc here, you can always click on this to go to this location. And this location contains the bad message, wrong serial key, try again. And also above you will find the good message, congrats, well done. And obviously these parameters are being pushed to the stack in readiness for the function call, the message box function call. So the message box function call, you can refer to the MSDN library. Go to Google and search for MSDN message box, and it will show you over here. It will show you the parameters for message box. So we have 4 parameters. So you have the windows, the parent window, the text, the caption, and the type. The type is whether you want it to have OK button, OK cancel button, OK cancel, and retry, I think, and also whether you want to put icons inside your message box. And normally the parent window handle will leave it at 0. The text refers to this. This is the text. And then the caption refers to the title on top here. So these are 4 parameters for message box. So if you take a look at your over here, you also have 4 parameters, but they are in reverse order. So this is the first parameter, this is the second parameter, this is the third parameter, and this is the fourth parameter. So these are the 4 parameters for this message box function. Same thing over here. Before you can call a function, you must first set up the parameters. So for this message box, this is first parameter, second parameter, third parameter, and then over here on top somewhere is your other parameter. Okay, so that's how it works. Alright, so now we are going to try to look at the graph view. Since we already got the function, we can go to graph and look at the graph view. So this is a function which decides whether to show the bad message on the right, wrong serial key, or the good message on the left, which is congrats, well done. So in the next video, we are going to put a breakpoint here and step through. So I'll see you in the next video. Thank you for watching. Welcome back. So in the previous lesson, we already managed to create the function. So we are here now. And now we are going to step over by putting a breakpoint here. Put a breakpoint and breakpoint here. So now we can run. So click OK again, and then click continue until it hits our breakpoint. Okay, so now it has shown the windows. Let's enter a wrong password, 112233. Click on check. So now it has hit our breakpoint, as we can see. So we can go and view it in the graph view. So let us step over now. So now it's coming down here. Okay, so now this is a crucial moment. It will come here and test whether EAX is 0. If EAX is not equal to 0, it is going to jump to 401154 and show the bad message. So let's see what happens. So now it is about to test EAX, and we can see in the register EAX is not 0. So EAX is -1. So that means it is going to jump here. So let's see that happening. There you go. It has jumped to the right. And now it's going to push all these parameters to the stack. This fourth parameter is already pushed to the stack here. Now it's going to push the third parameter. And the third parameter has been pushed to the stack. You can confirm it by right-clicking, show in hex dump, and you can see the third parameter, sorry, which is this one. Next is going to push the second parameter to the stack, so step over it and you can see it over here. You can also compare the address 411b08, 411b08, and then you can right click and show it in hex dump, and you can see this is the text, wrong serial key, try again, which is this text here. Next is going to push the first parameter to the stack. So let's step over it and watch what happens here. And the first parameter has been pushed to the stack. So this is the first parameter, second, third, and fourth parameter, and this corresponds to your documentation. First parameter is this. So 0 means 0 for this. So by right, this should be 0. So that is correct. If this thing is anything other than 0, then the message box will not show. So the first parameter has to be 0. And then the second parameter is this, the text. And then the third parameter is the caption, which is this. And the fourth parameter is the type of the message box, which is this. So they are being pushed to the stack in reverse order. So the fourth parameter is pushed first, and it comes over here. Next, third parameter is pushed, and it comes over here. Next, second parameter is pushed, and it comes over here. And lastly, first parameter is pushed, and it comes over here. So they are pushed to the stack in reverse order. This is always the convention in the assembly. So once it's pushed to the stack, your message box now will make use of all these parameters to show the message. So it's going to show the bad message. So let's step over. And there you go, it shows the bad message. So now what I want you to remember is the parameters. First parameter is very important. It has to be 0. If this first parameter is not 0, the message box will not show. Remember that. Okay? So next video I'm going to show you how to reverse this jump so that it will not show the bad message. It will show the good message. But in the meantime, I want you to remember so with that, I'll see you in the next video. Thank you for watching. Welcome back. In the previous lesson, we've already seen how this thing works by debugging it, and we saw that it went to the right to show the bad message box. And I also reminded you that before a message box can be shown, all the first parameter must be 0. Right? And I also showed you how to make use of the MSDN documentation to understand the parameters and how the parameters are being pushed to the stack in reverse order. So remember, the important thing is first parameter must be 0. Okay, let's see why. So now I'm going to stop this and I'm going to start again. I'm going to go to the breakpoint. I'm going to go to my function here. I already got a breakpoint there. So I'm going to run it now. And click continue. Click continue again. Continue again. And now it has shown. Let us enter a wrong serial key 112233. Click on check. Okay, so now it has hit our breakpoint. We go to the graph, we can see it. And now we step over. We are going to step over until it comes here, and we are going to reverse this jump to show the good message. Okay, so now over here, we know that it's going to go here, but we don't want it. So now, let me ask you a question. In order to reverse this jump, can we do this? Right click and just edit, reverse the jump. Yes or no? That is the question. The answer is no, it will not work. Why it will not work? Because, as I mentioned to you just now, the 4 parameters for your message box, the first parameter must be 0. First parameter must be 0. So now over here, the 4th parameter has been pushed to the stack. Okay, so now let us now reverse the jump and just see what happens. So I'm going to go to the set mode, set to cache mode. Now if you set to write mode, it might write it permanently. If you just want a temporary write, then you just use cache mode, so that after you quit the debugger, it will revert back to the original. It will not make it permanent. So that's why we use cache mode. Will not be 0. Let me show you. So let us reverse this now, and then go to the edit, and then over here reverse the jump, so it becomes JE. So let's step over, and now it goes to the left. See that? So it's going to say congrats. It's going to push congrats to the stack, but notice that earlier on it has pushed the 4th parameter, which is this. So step over this, it pushes this to the stack at this location. So this is the caption, and you can also confirm it by right clicking, showing it in hex dump, and here you go, congrats, you can see that, congrats. And now it's going to push this to the stack, second parameter, step over it, and the second parameter has been pushed to the stack at this address, right click, show in hex dump, and there you are, well done. See that? Well done. And finally, it's going to push the first parameter to the stack, but the first parameter is EX and EX is not 0. That is the problem. Okay, so if you step over this, it pushes -1 to the stack. So -1 will cause the message box to fail. It won't show the good message. Let's try it and see what happens. Step over it and run all the way, and you see nothing shows up. The good message does not show up. Alright, so that's why we cannot have a -1 as a first parameter for message box. So let's try again. We are going to stop this debugging. Okay, so our breakpoint is still there. So now we are going to set this to the cache mode and run. Keep on running until we hit our breakpoint. So the dialog, the window has shown. Let us enter the wrong password. Click check. So you see our breakpoint. Let us step over it. You can view it in the graph view. Okay, so now we are here. It's going to push the fourth parameter to the stack, so we step over it, and the fourth parameter is there. Then it's going to jump to the right, but we can modify this to make it not jump to the right. We want to go straight. So if you look at this assembly view, we are now here. If it does not jump, going straight will mean that it will show the good message. So how can we make it go straight? One way is to no opt this, but at the same time we need to take care of EX because we want the first parameter to be 0, not -1. So to solve that, we can use XOR EX. So XOR EX will remove this jump. At the same time, we will ensure that EX becomes 0 because EX is going to be pushed to the stack over here and it needs to be 0. So we can now right click this and then edit this and the instruction. We see that the jump not equal is 2 bytes and XOR EX is also 2 bytes. So we do this XOR EX and we can see it is also 2 bytes. So click OK. So now we can be sure that after this, EX will be 0 and at the same time, because there is no more jump, it will just go straight. So let's step over and you can see it has gone straight to the left. So now we can see fourth parameter has been pushed to the stack. Let's step over the third parameter. Third parameter is on the stack. Step over the second parameter. Second parameter is on the stack. And now the first parameter. Step over it. And the first parameter is now 0. So that is what we want. So now the 4 parameters are correct. So the message box should show. So let's step over and see it. And there you go. Congrats. Well done. Alright, so this is how you can solve this strike me. So now we know we can put a command here. Add command. Say XOR this. And then we can stop this. And now we can make it permanent by going to File, Set Mode, Write Mode. And then go back to my function and scroll down and look for this. Right click, edit, and then here we replace this instruction with EX, XOR EX, EX. Click OK. There you go. So now we can save this project, accept the default name, click save, and then we can close it. Save. Alright, I hope you have made a copy of it before you start writing to this, which I already explained is important in case you made a mistake. Okay, so now let's try to run this and see whether it works. We can enter any wrong serial key. Click on this and it will show you the good message. So we have solved this crack me by patching it. So that's all for this video. Thank you for watching. Hello and welcome back. In this video we are going to do serial phishing. So serial phishing is a technique where we try to analyze or debug the code so that we can get the actual password or the actual serial key. So in the previous lesson we've already created this one. We patched this to make it jump to the correct good message box whenever we enter any wrong serial key. So let's rename this now to version 1. And then we'll make a copy of the original and rename it back to its original name because we want a fresh copy. Now we'll open Cutter and open this previous project file which we have saved. So the project file is over here, GUI crack me. And it will automatically load the fresh crack me. So if you look at the comments, this is where we left our previous comment that if you wanted to solve this, we can XOR EX, EX. So now we are going to do serial phishing. So for serial phishing, we can do a static analysis first. So from here we'll see this is where you get the function called getDialogItemText. So getDialogItemText is where you extract the text content from a text box, and this normally will be an input text box. So you can look at the documentation for getDialogItemText. We go to Google and search for MSDN getDialogItemText and click on the link. And over here you will see that there are 4 parameters, 1, 2, 3, 4. And the second one is, the third parameter is the LP string. And LP string is the buffer which receives the text. So if you look at the code here, the third parameter should be this one. This is the first, this is the first, this is the second, this third parameter. So this will be pushed to the stack. And this third parameter comes from this variable. So after getDialogItemText has saved whatever the user enters onto the stack in the EX register, over here you can see that it will then load a string to ECX. So this seems to be like a suspicious text. Looks like a serial key. So it's moving to ECX, and then somewhere down here you can see that it is comparing the byte, the first character in ECX with DL, and EX is the buffer which came from dialog-item-text. So it is comparing what the user enters with whatever the actual serial key is, and then it goes in a loop. you can see down here, there is a loop going back up again and again. So each time it loops, it increases the element in the EX by 1. It also increases EX by 1. It's over here. So it increases by 2 bytes, presumably because it is Unicode. So Unicode takes up 2 bytes. So every time it loops, it increases by 2 bytes so that it will go to the next character. And then it will compare with the next character between ECX, which is the actual serial key, and EX, which is what the user enters. So if the first time it compares, if the first character is correct, it will proceed. Anytime it finds the first character is wrong, it will quit, go back out here. And then if the second character is correct, it will proceed on and on and on, and keep on looping. So this is how the program compares whether the serial key is correct. It compares it character by character. Now whenever you see a structure like this, the path that is longer is a good path. The path that is short and quick is usually the bad path. It means something has gone wrong. So this is how you can more or less guess that this going through the long path is good, and it is comparing character by character because there is a loop and because there is a counter here which increases, and you are testing here. You are testing whether DL is 0. DL 0 means you have reached the end of the string. Now in programming, the end of the string is a null terminator which has a 0 byte. So here is where it's testing whether you have reached the end of the character, whether you have reached the end of the string. So if you see 0, then it quits. It goes out and exits. And then, so now we know that this is probably the password or the serial key. So we can make a note. We can also search for this in the strings here. So we go to strings here, search for the serial key CR4, and we can see there. And if we right click on this, show cross-reference, we can confirm that indeed it is loading this string into ECX for purposes of checking. So most probably this is the password, so we can copy this out, copy and put it in a separate notepad. So this is probably our serial key. So this is a simple one. We managed to get it. So now we can test our program. We can run it and enter the serial key, paste it here, click check, and we got it right. Well done. So this is how we can do serial phishing by using static analysis. You can also do by dynamic analysis. So to do that, we put a breakpoint here, right click on the function that we have created earlier, and then put a breakpoint, and then run. Click OK, click OK again, and then click continue, click continue again, click continue again, and now the Windows has popped up. So just enter any wrong serial key, 1122334455, click check, and it has hit our breakpoint. So now we can go and step over. Okay, so now it's going to get the dialog item text. We entered 1122334455, and it's going to save it in the third parameter, which is this one. So we can right click this, show in hexadump. Now it's blank. So when we step over this call, it should populate this with the string we entered. So let's step over, and indeed, so you can see here 1122334455. So that is correct. So EAX over here stores our string that we entered, and then later on, you use this loop to compare byte by byte, starting with the first byte 1, which is in hex 31. So now let's move on, step over, continue to step over, step over. So at this point in time, it has loaded this string to ECX. So if we go to ECX, we got the address, so we can right click show in hexdump, and you can see here it has loaded the serial key cracking lessons into the memory in the ECX. So that means ECX now has got the actual serial key, and EAX has got whatever we typed in just now. Okay, so now you're going to step over, and now it's going to compare the first character C with the first character of what we entered, which is 1. So if you look at DL is the first byte of EDX. DL. Let's step over this first. So now EAX is what we entered, and the first byte is the hex 31. And hex 31, as we have seen, is the number 1. And number 1 is what we entered as the first character in the text box. And then now it's going to compare ECX with that number 1. And look at ECX. ECX is C. So is C equals to 1? No. So the comparison is to compare whether they are equal. So in this case, it's not equal. So now, because it's not equal, jump not equal will be true, and it will exceed the loop. It will exceed the loop, come here. That means, let's step over, and true enough, it has exited the loop by coming here. So this confirms that indeed it is using a loop to test character by character, whatever we entered. So we can now terminate this by stopping it. And then to test our hypothesis that it is indeed a loop, we can continue to debug again. And then run, click continue again, click continue again. And now we are going to enter the correct serial key in here. So we just copy this and paste it in here and click check. So it has hit our breakpoint, and now let's go through. Okay, after the call to get dialog item text, what we entered will be saved in EX because EX is the third parameter. So EX has been pushed to the stack, over EX was pushed to the stack. I think we missed it. It's one of these. Third parameter should be okay, we missed it. Let's try again. So we paste our correct key, click check, and then we go to our graph, step over, step over, step over, step over, step over. So now the third parameter is this one, third parameter for get dialog item text. If you right click this, show in hexdump. So watch what happens when we step over. So it has loaded the string that we typed in over here. Just now we entered this string, so now it is loaded into memory over there. So this is what is going to use to compare with the actual string inside ECX. So let's step over, continue. Okay, now it has loaded this string to ECX. So if we open another window, another hex window, add hexdump, pull it down here. So we have suppose have two hex dump. The first one is here, second one is here. We are also going to unsync this. So we need to go back to our main function, to our myfunc. Okay, so now we are here. So in the first hex dump is what we entered, and then the second hex dump we are going to look at ECX. So ECX is here, so we right click, make sure you select the first hex dump, this one, and then go to ECX and follow in hex dump 0. Hex dump 0 is this one, so follow this in hex dump 0, and this is the actual password. Compare it with this one, this is what we entered. Okay, so now it's going to enter the loop where it will compare character by character. First character compared, this first character is A from here, EX, which is pushed to the stack, and second character is, and the first character from ECX is from here, which is in ECX. So now we step over, and it is moving EX to DL. So EX, remember, is what we entered. So now DL has got the first character 63, which is character C. So if you want to know what is the conversion, you can use hex to ASCII, and you can see hex to ASCII. If you enter hex 63, hit enter, and you should get C. Alright, so it's comparing C, this C here in EDX. So DL, remember, is the first byte of EDX. So it's comparing C with, is comparing whatever you entered in EX, which is over in DL now, with the first character in ECX, which is the actual serial key. So this would be true because they are actually equal. Both are C in here coming from the EX, and C in the actual password. So we step over. So jump not equal will be false, it will go straight. And true enough, it went straight. So this will keep on continue, it will test. And then over here, he's checking whether DL is 0. It is not 0 because DL is actually C. So it should go straight. If DL is 0, that means end of the string, it will quit the loop. So in this case, it won't quit, it should go straight. And now it's going to compare, it's going to move the second character to DL. So over here is the second character. And it's going to move the second character of what we of the actual password to DL. It's going to compare the second character of the actual password with DL, and this time it's also going to go here. If it's not the same, it will quit. So step over and it should go to the left. Okay, now it's going to increment and it's going to test again whether we have reached the end of the string. Since it hasn't reached the end of the string, this test will be false, so it will go up to the top for the next loop. So true enough, it went up to the top. So this process will keep on continuing until it reaches, until DL becomes 0. DL becomes 0 is actually this, the null terminator, which is 0, 0, as you can see here. So once the null terminator is reached, this test DL will be true, and it will go straight and exit the loop. So this is proof, confirmation that this program is using a loop to compare the two strings. So let's confirm also that our password is indeed crackinglessons.com. So this is how we can use static analysis and dynamic analysis to do phishing for the serial key. Thank you for watching. Hello, welcome. In this video, I'm going to show you how to install Cutter for Linux. I'm using Remnux, an Ubuntu version, and it is a free version you can download as well. I type lsb-release-a, and you can see the version is listed here, Ubuntu. And Remnux is used for malware analysis and reverse engineering, especially for that. And this is where you can download Remnux if you want. You can also use Kali Linux or other Ubuntu. So Remnux is a Linux toolkit for malware analysis. You can click on download button and scroll down. You can see general OVA or VirtualBox. Get the VirtualBox OVA. Click on this link here. So this one is for import into Oracle Virtual Machine. So after you imported into Oracle Virtual Machine, you can boot, and here I am going to now open my Firefox because I want to download Cutter. So go to Cutter website and then click on the download button. So just click on download. After you finish downloading, it will be found in the downloads folder. I've already downloaded it, so it's already in my downloads folder. So go to your folder, and here you open your downloads folder, and you can see there Cutter version 2.05 64-bit. Now click on the documentation and it will show you how to install it. First thing you need to do is to add the executable permission to it by typing this command chmod +x. That will make it executable. So go to a terminal and navigate to the downloads folder. But before that, I'm going to cut it and put it in my home directory in a new folder. I'm going to create a new folder and call it Cutter, and I'm going to dump the image in there. So now I'm going to go to my terminal and navigate to my new Cutter directory. And then I'm going to ls and make sure it's there. And I'm going to type ls-l to see the full listing so that I can see the permission bits. Presently it is not executable, as you can see. Now I'm going to add the execution permission by typing chmod followed by the Cutter image, and I'm going to hit enter. And then I'm going to repeat the ls-l and confirm that it is now executable. As you can see, rwx means it's executable. So now I can run it by typing / followed by the Cutter name and hitting enter. And it asks me whether I want to import from a previous version of Cutter. I say no. Why does it ask? Because it already has a previous version of Cutter, an older version, a much older version, which is version 1 point something. As you can see from here, if I scroll down, I go to the last button and I click, I can see there's an old version already there. So this is already out of date. That is why we are downloading the latest version. So what we are having is the latest version. What we have downloaded is the latest version, version 2. So no need to import anything, just click no. So now it launches and you can click the, you can see it's version 2.0.5. You can also change the theme to darker theme if you want, but I'm just going to leave it at native. So click on continue. And over here you click the about button and you can see confirm that it's version 2.05 and it's using a Resin engine instead of Radare 2. Resin is a fork of Radare 2. So the Radare 2 commands also work for Resin. So that's it. So this is how you install Cutter for Linux. And remember, you can also use Ubuntu, other Ubuntu versions, or you can also use Kali Linux to install Cutter. So long as a Debian version of Linux, it should be fine. So that's all for this video. Thank you for watching. Hello and welcome back. For our first Linux Crack Me, I'm going to recommend using this one from CrackMe's one. So I've already provided this for you in the resource section. You don't have to download here. So this is giving credit to the author. So this is the author for the CrackMe. So go ahead and download the CrackMe from the resource section for this lecture, and then we'll continue. Thank you. As you can see, I've got two virtual machines, Windows 10 with Cutter and Remnux Linux with Cutter. So I've already started my Remnux Linux, and here it is. And now I'll go to full screen. So go and download this project. Linux CrackMe 1. Unzip it and put it in the folder called Cutter Projects. And inside Linux CrackMe 1, there is one file. So this is the executable. It's a Linux executable. So before you do anything, make a backup first. So just copy and paste, and so now you have a backup copy here. So now we can test this and see how it runs. Just right click, open in terminal. So now we'll go to test this. First we do an ls-l to see whether it's executable, and we can see it is because there's an X there. So this is executable file. So now we want to know whether it's a Linux binary. So we use the file command and hit enter, and we can see that it is ELF64-bit. So this confirms that it is a Linux binary. It's a Linux executable file. So to run it, we just type // and then followed by the file name and hit enter, and it tells you the usage. So we are supposed to run it with a parameter, with an argument. So the argument is the password. So we can give any password we want because we don't know what it is. And we hit enter, and it says try again pal. That means it's a wrong password. So now we are going to crack this, doing a static analysis first. So we go to our home and go to our Cutter folder where we put our Cutter image. So we just double click this to start Cutter program. So now you can see we have the Cutter here. We can select our CrackMe, which is this one. So we just click select and click the CrackMe, click open, and then click open again. Make sure analysis checkbox is checked and click OK. So now let us try to change the view to a theme, a dark theme. So let's go to edit, preferences, and then appearance. Let us change this to midnight just to see what it looks like. Then click OK. Okay, so now this is the graphical view. You are at the entry point, entry 0. So double click to go to main. So this is the main function. You can use your scroll wheel on your mouse, press Ctrl key and hold it down, and then zoom using the scroll wheel. Then you can drag around as well. Just left click and drag. Alright, so now you can see I'm just going to make sure I'm in the default view, reset to default layout. So now you will see on the first tab, dashboard, it shows you the format is ELF64, which is a Linux binary file system, and then bit 64-bit ELF64. The size and the architecture of my Linux OS is 64-bit architecture, and this program is compiled in C language using the GCC Ubuntu compiler. And here you can see the analysis information and so on. So this left panel here shows you all the discovered functions for this Linux binary. And you can also go to disassembly view to see it in linear view. So this is the disassembly view. And then this is the graph view. like this. And then if you go to strings panel, you can see all the strings that has been discovered for this binary. And it is interesting to note that this string is saying good job now, keygen me. Then below that, try again pal. If you just wanted to go ahead and look for this good job, just right click, select cross reference, and then you will see where the good job is being referenced inside the assembly. Then if you double click this, you can just go there directly. Good job. Now you can keygen me. Alright, so this takes you back straight to the main function. So you are in main function, which is this one. So let us try to do a preliminary overview. So here you can see there is a start of the function, and then these are all the stack references for the various variable names. RBP is a base pointer for the stack, and then this is offset to the stack from the base pointer. argc will be your argument count, argument vector. So argument count is how many arguments are inside the when you run the program, how many arguments are there. And then RV is the argument vector, the array which holds the argument itself, the parameters. And then here you can see there's a branching to the left and right, and this one seems to be a bad message. This one seems to be okay. So when you go to the left, the shortest path is usually the bad path. The good path is usually the one which is longer. So the left one is definitely no. Same thing when you come here. If he suddenly goes to the left and take the shortcut, that means something has gone wrong. But if it goes into the longer path, that means this is the right one. You see that? This is how you analyze. Then when you come here, again, the short path is the bad one because you immediately go out, and the long path is usually the correct one. And when you come here, it's the same thing. If it goes to the shortest path, it means there's something gone wrong. If it goes to the right, the longer path, it means something good. So this is the basic rule of thumb for graphical analysis. When you look for the correct path, look for the longer path, not the shorter path. Shorter path means something gone wrong. Alright, and then finally at the bottom here you can see string good job, keygen me, and here call fail. So if you double click on call fail, it will take you to the function which shows the bad message. Sorry, try again pal. This is the bad message we saw. Now how do you go back? Press escape and it takes you back to the previous graph view. So the escape button takes you back, okay? And then alright, so you go to imports and you can see all the imported functions. This is a standard C function, put string, and string length is to measure the length of the string, how long it is. So it seems that it's a very small program using only two C functions, main functions. Okay, so and then in the decompiler view, you can see the decompiled main function as well, and you can see something interesting here. It is checking for how many arguments. So if you didn't enter any parameter, the argument count will be 1. So when argument count is 1, it will go to the else part here and print the usage password. As you can see here, usage password. That's what we saw just now when we didn't enter any parameter. However, if you enter two parameters, that means the program name and the argument, then this will be true, so it enters the if loop, if block, and then goes on to process it. Okay, so next lesson we are going to analyze this in more detail. Now I just wanted to give you a high-level overview of what the Linux binary looks like in the first look. So I'll see you in the next one. Thank you for watching. Hello and welcome back. So now we are going to do a static analysis and see how we can solve the correct me. So go to the graph view, and then from here you can see that initially we saw that it is trying to check whether there are two parameters, whether there are two argument counts. So it seems like it is doing it over here, comparing. So you can see from here, argc is actually this variable, so we can rename this. So we can rename this by right clicking this, and then rename local variable var24, or you can press N as a shortcut key. So we can rename this as argument count, arg count. And then this one is argv, so we can rename this, right click and rename this as argument vector. Vector means array. So don't worry if you wrongly give a name, you can always rename it back later. And then here it seems it's just moving 0 to it, so let's rename this variable as 0. So renaming variables is highly recommended because it makes it easy for you to understand and easier to analyze the code. So now you can see down here clearly it's comparing whether the argument count is 2. So if you had entered a parameter here like this, that means argument count is 2. If you didn't enter a parameter, the argument count is 1. That is the meaning of argc, argument count. And then whatever parameter you entered here will be stored in argv. So the array stores the string that you enter. So this is the argument vector which stores a string. So now it tests if it's equal, then it will jump to 1175, which is here. If you didn't enter an argument, then it will go to the left and say, give you the usage, how to use the program, which we saw over here, usage. Then if you want to take a look at this string, you can double click on this, go to this assembly, and you can see here, string, usage, password. So let's go back to the graph view by clicking main again. Okay, so now let's take a look at this part. So assuming we entered an argument, so now you go here and it's moving your argument vector to Rx, and then it is doing something with the argument vector. It's trying to access one of the members in the argument vector, and it's doing that by putting in +8. I'm not sure why it does that, but definitely it has to do that in order to access your argument vector. Now in C programming, argument vector 0 is the name of the program. Argument vector 1 is the parameter. But here it's putting 8, but there is no 8, so I'm not sure why it puts 8. But anyway, if you're not sure, just skip it and look at what you can understand. Over here is calling the string length. So in C programming, string length is to measure the length of the string. And if you want to refer, you can go and check out C string length. And it will tell you all about what is string length over here. So string length will measure the length of the string and return a value. So anything that is being returned is stored in the register EAX. Okay, so here is returning the register in RAX. RAX is 64-bit register. EAX is 32-bit register. So if your program is a 32-bit program, you'll be seeing EAX. But for 64-bit programs, there will be an R instead of an E. So obviously, it is trying to compare whether the string length is 9. I believe RAX is referring to your password that you enter. So you can go back on top and try to guess. In retrospect, you can see that RAX is from here, and RAX is moved to RDI. So RDI must be the parameter to the string length, char s, because as you remember, all the above instructions that come before a function call are preparing for that function call, is a parameter to that function call. So typically RDI or EDI in 32-bit programs stores strings. So, and where does RX come from? RX comes from S. And where does S come from? From RX. And this RX comes from this offset, so we can guess that this S is actually the input string. So we can rename it now, right click rename and call it input string. Input string. Like that. So now we know RAX eventually came from input string, and RAX is sent to RDI, and then string length measures the length of RDI, which is the input string, and then tries to compare it, whether or not this RAX, which is actually input string, is 9 characters long. So from there we can guess that it is looking for a password which is 9 characters long. So we just type it out first, 9 characters long. And then over here, if it's 9 characters, it goes to 11AB, this address. Otherwise, it goes here and call field. So double click on call field and you will see that it is a function to throw the bad message. So press escape to go back. So definitely we don't want to go left, we want to go right. So we make sure that your password is 9 characters long, then it will go to the right. Next, it is going to take your input string and move it to RX, and then it is going to look at the 5th character of your input string by moving the offset to the 4. Now in C programming, the first element of an array starts with 0, and then the 4th element is actually character number 5. So it's looking at character number 5 and then seeing whether or not it is this character 2D. Okay, so what is character 2D? If you want to know, you can go to this website and then rapid tables. You can search for it. Just search for hex to ASCII converter. Click the first one and then you get this. So over here you can put in 2D and then convert it to hex, and you will see that it is dash. Okay, so this is the ASCII code for dash. So that tells us that it is checking whether the 5th character is a dash. Okay, so input string goes RX, and then it moves the pointer to the 5th character, and then it copies that particular character to EX, and then compares whether the character is this dash. So AL is the first byte of the EX, and then EX is the four lower bytes for RX. So over here it is adding 4 to move it to the 5th character, and then once it's there, it will move that particular character into EX and zero out all the remaining bytes, so you only have 1 character inside EX. So once you have zeroed out, the last character there, which is the last byte, is AL. So you can compare it this way. So if it is equal to dash, it goes here. If not, it goes here and call fail again. So now we know the 5th character is the dash. That's a password. 5th character. Alright, so next thing is goes here. If you have entered the dash for the 5th character, it will go to the right, and it will move 0 to this variable. So we can rename this variable as 0. So we call it 0. Okay, I think we have already used the variable 0 before here, so we call it 02. So we are calling this 02, right name, rename varchar1 as 02. Alright, so now we know that this variable stores 0, then straight away we jump to 11F3, and then we move 0 to EX. Now when we look at something confusing like this, we don't know what it's trying to do, straight away go to the function, and that will give you a sense of what is happening. So it's trying to compare another string, which is an RDI. And RDI comes from RX. RX comes from input string. So again, it is testing the input string the second time. Alright? And it is comparing with RBX. And what is RBX? RBX comes from here, and RBX comes from EX, and EX comes from 0. That means RBX is 0. So in this case, it's comparing whether RBX is below RX, that means less than RX. So which is the bigger string? RX is the bigger string because RX is your input string, and you know that RBX is 0. Therefore, this JB will be true. So it will go over here at this address 11D4. So in this address here 11D4, it will move 0 to EX, and then over here it's going to compare something else. It's going to compare one of the character. So which of the character is it trying to compare now? So let's find out. So it moves 0 to EX, and then move EX to RDX. Therefore RDX is 0. And then after that, it moves the input string to RX. So RX now contains your input string, and RDX contains 0. So, and then it adds RDX to RX. So what is it trying to do is create an offset. Okay, so your RDX is your offset, and then your RX is your input string. So when you add RDX to RX, that means it's trying to enter the correct element of the array. That's why you add. So now, since RDX is 0, that means it's accessing the first element of the array. So it's checking for the first element of your string. And then it's trying to compare that with this var1dh. So what is var1dh? Look for it. var1dh is, I think, here. var1dh. And it is moving this character to var1dh. So what is var1dh? Let's go back to our hex stack converter. Convert 40. So convert 40 in hex to ASCII, and you get this ampersand character. Now this alias character, sorry. So it is looking for this character. So let's rename this. Rename this variable alias character. Call it alias character, or give it a better name. Rename alias to alias char character. Alright, so now we come back here. It will make more sense. It's comparing whether AL, which is your first character in your array, is comparing whether the first character is an alias. Therefore, this should be your password for the first character. So now you have already figured out the first and the fifth character. First character is alias, and fifth character is a dash. So now with that, if it is not equal, then you go to 1EF, and then it goes out here to do something else. We are not concerned. But if it's correct, then you go to the longer path, come down here. And then from here, you move 1 to this 0 array. So now we rename this. We rename the 0 to 1. So now this becomes 1. Alright, so now that we renamed to 1, we know that this variable holds 1, and it jumps straight here. And then it moves 1 to EX, and then it XOR 1 with 1. So when you XOR 1 with 1, you will get 0. Then when you test AL with AL, definitely it will be 0. So jump equal will go here. Good job. You have solved this. So this is how you solve it using static analysis. Let's confirm it. So we know that this is probably the password. So we try to key it in and see where it works. Good job. Now keygen me. So we have solved it using static analysis. So that's all for this video. In the next one, we'll look at dynamic analysis. Thank you for watching. Hello and welcome back. In this video, I'm going to introduce a new feature in Cutter known as reverse debugging. Reverse debugging is the ability to step backwards when you are doing debugging. So let's open our Cutter now and then select the Crack Me. Click OK. Go to the main function. Now I set this back to the native view rather than using the dark or midnight view, because when you are debugging, it is easier to see the highlight when you step over. If you are using the dark view, it's difficult to see the highlight. So now we put a breakpoint on the start of the main function, which is to push RBP, by right clicking and adding a breakpoint there, and then we run. Click OK. Enter the arguments 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Click OK. And then click on continue until you hit the breakpoint. So it has hit the breakpoint. Let's go to the graph view. And then now, in order to enable reverse debugging, you need to click on this button here called Start Trace Session. So now, the moment you click on that Start Trace Session, you will see this additional button, Step Backwards. So this is called reverse debugging. So let's try it and see. So now we step over one by one, line by line. Let's go to graph view. So now you're here. You can see over here, it's highlighted. And then step over again, and now it's here. So you can see the highlighting in blue. So this is only possible in the native view, which is a light view. If you use midnight or dark view or the dark theme, it is difficult to see this because this will be brown or red. So red in a dark background is difficult to see. So that's why I switched back to light view. So now we step over. Now notice when I can click this button now to step backwards. So when you step backwards, the stack and the registers and as well as the hex dump all follow suit. So you step forward, you notice the registers as well as the other things changing. So now you come to this line. So this ability to step backwards is useful when you want to identify which of the memory address in the stack this refers to. RBP minus 24, you do not know which one is RBP minus 24, but if you step forward and step backward, you can see the change over here. So step forward and notice the change here when I step over this. Notice something has changed. Now you can step backward and confirm it. This one has changed. This value here has changed. That means this address here somehow related to this RBP minus 24. So this is useful. So you can help you to identify which memory in stack refers to the offset here. So now you know that RBP minus 24 refers to this. You can actually right click this and show it in your hex dump in unsync. I have two hex dump open. This is unsync and this is hex dump 0. This is hex dump without 0. So these values here refers to this in reverse order. So the list in this address 38 here refers to here D38, and 60 is the least significant byte, which refers to 60 at the back here. and then 56 is the most significant byte, refers to 56 here. This is because the Intel convention uses something called little endian, where the least significant byte appears on the left and the most significant byte appears on the right. So when you see 5631 and so on up to 60, in the memory itself is reversed. It reads from the right to the left. 56331E and so on is actually over here 5633 and so on. Reverse order. So over here now, you can analyze what happens when we step over this. Since we are already at this address D38 over here is pointing to 60, the last one. So now we step over this, watch what happens to this. See that? This thing changed, 02 change. That means it's pushed 2 to this address. RBP minus 24 is referring to C. D3C 02, this one. Let me step back. Let me step forward. And you can see it changing. Yes? C. So this is how useful the reverse debugging can be. It allows you to pinpoint which part of memory exactly the changes are being made, as well as which part of the stack is corresponds to the offset that you see here. So let's step over the next one, RBP minus 330. We don't know which part of the stack this offset refers to, but we step over this, we can see it. Now watch the stack again when I step back. So this one has changed, right? So this refers to this RBP minus 30. Let's confirm that. Yes, indeed, this thing has changed. So we can right click this and go show in the XDUMP, and you can see here D30 is referring to here, D30. This 58 is referring to this 58 here, and then this 7F is over here, 7F. So this is the address. You read from the right to the left in reverse order. You get it here. 7FF D7 up to 58 is referring to this in reverse order. So at this address D30, which is here, D30, you are storing an address. So this is an address of another location in memory. So that is how you can identify your location in memory based on this forward and backwards, stepping backwards and forwards. So next one is now it's going to push 0 to 1E. So let's step over. So it pushes to 1E. Step backwards. Step forwards. Okay, you can't see it changing anywhere here. That is because probably one of these zeros here somewhere is already the 0 that is pushing to. So never mind. Later on in the next lesson, I will show you how to use the Resin console to print exactly the address of this offset inside the console. That will be the next lesson. So for now, I just want to show you how to use the reverse debugging. Next is going to compare 2 with this location in memory. So let it compare. So since you entered 2 parameters, it's going to go to the right. So it's going to move this to RX, step over. Step over. Okay, so now this one, keyword RBP minus 8. Which part of the stack is this offset referring to? So let's step over and see the changes here. Yes, do you see this thing change? Let's step backwards. Yes, this one changes, right? That means this one is referring to RBP minus 18. Try that, confirm again. Step forward. Yes, correct. See that? So we can actually right click this and show in hex dump. And here again we can see the cursor stops at this address 408. 8, which is referring to 4, 8 over here. 4, 8. Okay, so 4, 8 refers to B7, which is the least significant byte. So the most significant byte is 7F, which is the most significant byte here. So this whole thing, 7F up to B7, is referring to this. Alright, that's how you should view it. So that is what is happening here. It's a Q word, meaning 4 bytes. Q word is 8 bytes, sorry. D word is 4 bytes. And word is 2 bytes. Okay, so the next one is going to push this ASCII code 40 to this location, and it's just going to occupy 1 byte. So let's step over and see that happening. Yes, do you see this thing change? That means this address is referring to RVP minus 18. Let's step back and confirm that. Yes, see that? It goes back to 0. If you step over it again, notice what happens? Yes, so this one refers to RVP minus 18. So we can confirm that. Right click. Let's right click and go hexdump, show in hexdump. And you see 400 refers to here 00. So this 00 here is actually this one here. So where does 40 come? 40 is pushed in here, right? So this whole thing here, from here to here, 1, 2, 3, 4, all this refers to this 40, 40, 40, 40, 40, 00, 00, 00 in reverse order. Is friend to that. You can confirm it. If you step backwards now, you see this thing reverting to its original value. But when you step forwards, you see 40 is written here. Why? Because over here you're only overwriting 1 byte. So 1 byte is 40 is 1 byte. So every 2 digits like this refers to 1 byte. 1 byte, 1 byte, 1 byte, 1 byte. So let me step backwards. 00. Okay. Now if I step forward, 40. See that? So this 40 is actually at 403. The address 7FFF doing and so on. D4 D43. D43. Alright? But here the address is 40. So 40 is actually the start of the byte. So you have to move back 3 bytes, 1, 2, 3 from the back 1, 2, 3 bytes to reach 40, because this is reverse order in Little Endian Intel convention. So 40 refers to the least significant byte. Then you have to move back 3 bytes to reach the 40. Same thing here. This 40 refers to this last byte here. See, the least significant byte. You have to move back 1, 2, 3 bytes to reach 40. So at this 40, the actual address is not 40 but 443. See that? 4, 3. Right? That's how you calculate it. Okay, so let's go forward now. Step forward, and so on. Alright, so this is how you can use the reverse debugging to allow you to do things which you normally could not do easily using a debugger. So that's all for this video. Thank you for watching. Hello and welcome back. In this video, I'm going to teach you how to use the Reason console. So let's open Cutter. Open the Crack Me. Click OK. And then here we go to the main function. We select our push RBP, which marks the start of the function. And then we add a breakpoint here by right-clicking it, adding breakpoint. Then we run. We click OK. we enter our command line arguments 1, 2, 3, 4, 5, 6, 7, 8, 9. Click OK. Now we click the continue button until we hit our breakpoint. So it has hit our breakpoint. We go to our graph view and we turn on reverse debugging by clicking the start trace session button. So now this back button is available, step backwards button is available. So now we can step over, go back to graph, step over, and then over here, continue to step. So now it is about to push EDI to this stack. So we can step over this now. Now we can use the console to view what is the value stored at this offset. So to do that, we need to open the console by clicking Windows, Console, and down here you will see the console. And here you have the Reason console open. You have debuggy and you have Reason console. So the command, you can go and download this notes from the resource session. So Reason is the backend engine for Cutter, and Reason is a fork of Radar 2. Therefore, many Radar 2 commands also works in Reason. So if you wanted to get the value stored at this location, and you can see it is a byte, we can use Reason console to type in this command. So the command is as follows. We type P for print, and then X for hexadecimal, and then here we must put the parameter for the whatever output we want to view, whether it's in D word, or whether it's a byte, or whether it's a Q word, or whether it's a word. Byte, word, D word, and Q word, 4 possibilities. So here is a D word, so D word is 4 bytes, and then followed by this symbol. This symbol means at what address. So the address is RBP minus hex 24. So this means that I want to print hex, in this case 4 bytes, at RBP minus 24. So when you hit enter, you can see the output here, 02. So 2 is being written to this location, 7FF63 ending with 40EC02. So that confirms that the argument count is 2. Now let's move on to the next one. So we step over the next one, and we want to see what is being stored at that location. So we repeat the same command, but we change some parameters. Just use the up arrow key to go back to the previous command. And over here, the same one, px is the same. And here is qword. So qword is 8 bytes, so put 8. And then here, RBP minus hex 30. RBP minus hex 30. Hit enter, and you see it is storing this address. And we can also confirm by looking here. Let's step back. So this one is the address that we're interested in. So we step forward to see, and you can see 7FFFF63CC4208. 7FFF63CC4208. See, it's the same. So that confirms it. So these are the two ways in which you can examine their memory. Either you look at the stack and then trace it in the hex dump by right-clicking this, show in hex dump, and you can see the same thing here. Or you can directly use the Reason console and print out exactly what you want. So this is flexibility for you guys. you can use the reason console. Alright, so the next one is here. It's going to push 0 to that location, so we step over it. Okay, when you step over it, here doesn't show because it's probably one of the zeros which is already there. Step back, step forward, it doesn't show, right? But you can always use the console to look at it. So here now is a byte. So we need to change this to 1. We need to change this to 1, and the address is RBP minus hex 1E. RBP minus hex 1E. Hit enter, and you can see 0 is being pushed there. So 0 is indeed over there. The next one is to compare, so we just step over, and then it's going to jump to the right because we have entered 2 arguments. So we move to the right. Okay, let's continue the step over. Alright, the next one is going to move RX to RBP minus 018. So we step over. Now we can use the command to show the value stored there. So just pause the video and try to do this on your own. What reason command would you use to show the value stored there? Alright, I hope you have tried that. We use the same command, but this time it's keyword. So here should be 8 bytes. So and then add RBP minus hex 1D. RBP minus hex 1D. Hit enter. And we can see here at this location it has pushed REX there, and that is a keyword. Alright, keyword. So keyword is 8 RBP minus 1D, and you can also use this. Let's type back to see which one is it. Alright, here. So at this location, show in hex unsync, and it is this. So over here you will see it is RP minus 1D minus 18, sorry, it should be 18. Yes, 18. And there you see the same thing here. We are referring to this. Yes, RBP minus 18, not 1D, I'm sorry. So next one is this. So what is the RB minus 18? It is apparently a pointer. So if you want to see what is stored at that pointer, you need to use the dereference symbol, which is R. So you need to put an R here, and then hit enter. And you can see what is stored there is this string, the string that we entered. So this command R here is the dereference. You can refer to the notes. See, to dereference a pointer where the pointer is an address to a string, we must add, and here REX plus this is an address. So you need to type the additional command R here. R is for dereference. So remember, address is merely a pointer. So in this case here, at this address RBP minus 18, we have an address. So the address is actually stored at this RBP minus 18. In order to see what is actually stored at this address, we need to put an additional R here to dereference it. Okay, so that is a principle in computer science. A value stored at a particular address can either be an actual value or a pointer. If it's an actual value, you'll be able to see the number. For example, maybe it's a hex number, or maybe it's an integer, and so on. But if it is an address, that means it is a pointer. The word pointer means an address. So whenever you see an address stored at the offset, you need to put R here in order to find out what is the string stored there. So let's move on to the next one. Let's step over. Alright, since we entered 9 characters, it's going to be true, so you jump to the right. Okay, so let it move on. Alright, so now it's going to compare 2D with AL. So what is 2D? To find out what is 2D, we can use the rx command. So if you are using Remnux, you can use the rx command. Let me clear the screen. Type rx2 -s for string and then the hex 2D. So we are converting the hex to ASCII code, and you can see it's a dash. So 2D in hex, when converted to ASCII code, is dash. So if you don't have this rx command, it means that you don't have Radare2 installed. Here, if rx2 command is not found, you can install it by typing apt-get install Radare2. Then you will get the rx2 command. If you don't want to use that, you can of course use go to the Google Chrome and search for hex to ASCII converter and click on this button here, this link here, and you can type 2D convert and you still get the same result. So here you have another option. You can use rx2 command to do that. Alright, so now we know it is comparing something. It is comparing whether AL has got the dash character. So what is AL? AL, as we have seen previously, is the one of the characters inside the string that you entered. So the string that you entered is RVP-18, and to see that, you can actually type this command. RVP-18 is this one, and the string is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then when you add 4, that means you are moving the element to the 5th character. So first character is 0, second is 1, third is 2, and then 4, and then 5th character. So 4 here refers to the 5th character. So it's testing whether this AL here, which is the 5th character, you can see here AL 35. So again, 35 can convert to using the rx2 command. 35 is the character 5. Right? This is the hex and this is the string. So it's testing whether this 5 here is a dash. AL is 35 in hex. When converted to string, it is a 5. So it's comparing whether 5 is equal to a dash. 2D is a dash, as we have seen here. 2D is a dash. So this 2D here is referring to this one. And we saw that this 2D is a dash. And this AL here is referring to 35. 35. And AL is the lower byte for the AX register. So 35 converted to ASCII is 5. So it's comparing whether 5 is equal to dash. That means it's comparing the 5th character, whether this is equal to dash. So because we did not enter a dash here, it will fail. It will not jump to 1CB. It will go to the left. So it's going to go to the left. So we know that the 5th character is a dash. So we can stop this now and rerun. And this time we enter the correct character, which is a dash here. Click OK. And then we continue again until we hit our breakpoint. And then we turn on reverse debugging. And we continue to step until we come to the same location as where we stopped earlier. Okay, so now it's going to go to the right because we entered the dash for the 5th character. And step over, you go to the right. There you go. Next is going to move 0 to this location, so we step over it. And then we can see here that one of these changed. So step back, yes, this one. This one changed. So at this location, we can show in the hex dump. One of it will be 4 bytes from here will be changed to 0 because it's a D word. So we see which one is it. So we step over and we see here. This one has changed to 0. Step back. You can see the change, right? I think it's these 4 bytes. 1, 2, 3, 4. Step back and see. Nope. These 4 bytes. 1, 2, 3, 4. Okay, step forward. Step back. Step back. Okay. Now we are here. Step forward. You see that? These 4 bytes. We can see the same thing using the command in the Resin console. So we can type, so in this case, we are not going to dereference anything. So we remove the R. And this is D word, yes? So D word is 4 bytes. So we change this to 4. And the address is RBP minus 1C. Hit enter. And you can see 4 bytes. At this address, 54DC. So here is 5D4C, 5D4C, 5D4C. Correct, these 4 bytes. Okay, so this is how useful the Resin console can be to pinpoint and corroborate what you see in the hex dump and the stack. So it's moved 0 to here. So these 4 bytes became 0. So now it's going to jump straight. So now it's going to move this to the X. Let's step over. Step over, step over, step over, step over, step over, and step over. Alright, step over, step over, step over, step over, step over. Alright, it's going to compare AL with this. So what is in RBP minus 1D? If you've forgotten, you can always repeat the previous command. RBP minus 1D. Just step back. You don't have. Okay, fine. Let's enter it. BX. This is a byte. Byte. Okay. So byte is 1, and then at RBP minus hex 1D. Hex 1D. Hit enter, and you see at this location you have the hex 40, which corresponds to the string alias. So over here is alias, and it's comparing AL with that. So what is AL? AL is 31. And what is 31? 31, if you want to know what's 31, use the RX tool to convert 31. And you see 31 is 1. So 1 is the first character you entered. That means it is comparing the first character you entered, whether or not it is equals to alias. Why? Because AL is referring to 31 in hex, and 31 in hex is the first character you entered when you convert it. So AL is 1. And then this RBP minus 1D, from here, from this Resin command, you can see it is alias. That means it's comparing your first character whether it is an alias. That means your first character should be an alias. So we can stop this now and type it, run it again. So first character should be an alias. And you have seen before, this is indeed the correct format for the password. So this is how useful it can be to use the Resin console as an additional tool to help you do analysis for your binary files. So that's all for this video. Thank you for watching. Hello and welcome back. In this new lesson, we are going to use another new CrackMe, and I have downloaded it from this website. And you don't have to download from here. You just download the version that I provided for you. It's the same one. So this is just to give credit to the author of the CrackMe which we are going to use next, which is Lost Password Login. So after you have downloaded it, you unzip it and put it in this folder. The unzip password is crackinglessons.com. So inside it you will find the CrackMe here, and the credits to the author, which I just mentioned earlier. So now that you have this, we can open a terminal in here, and then the first thing we do is to check what kind of binary it is by using the file command. And then we find that it is also an L64 bit, and it is also executable. We can confirm that by typing ls-l, and we see there is RWX, which means the X means it's executable. So now we are going to run it and see what it does. So to run it, we just type // followed by the name of the binary, and we hit enter. And it asks us to enter the password, and we can just enter any wrong password. Let's say 123456, and we hit enter, and it says login failed. Now I'm going to show you how to use Cutter to begin the analysis of this program. So let's open Cutter. Before you do anything, make a copy of this so that in case you make some mistakes, you still have a copy there. So let's fire up our Cutter. And I've already done some analysis. So click on select, go to the folder that contains your CrackMe, so which is CrackMe 2 folders, and this is the one, and click on open, click open again. Make sure the analysis checkbox is checked and click OK. So now you can see over here are all the detected functions for this binary, and you can see it's using C++ libraries, quite a lot of them. Over here you can see strings. So this program is written in C++. Another place you can look is the dashboard tab at the bottom. So you click on that, you can see format is L64, and here it confirms it's C++, and the compiler is GCC Debian. Debian is the flavor for the Linux version that the author has used to run the GCC compiler. So here entropy 3.8, anything less than 7 means that it is not encrypted. So then here are all the summary, cross references, and so on. So there are two ways to analyze this. You can see earlier on, if you enter the wrong password, it says login failed. So one way to start off is to look for this string login failed. You can do that by going to strings, and here in the filter box, just type in login failed, and you can find you have login successful and login failed. So right click on login failed, show cross references, and here you can see we have the location in the program where this string was loaded, login failed and login successful. So we can double click to go there, and here it is, login successful on the left and login failed on the right. So this is where it loads the strings. On the right will be the string for login failed, and on the left will be the string for login successful. So if you wanted to patch this, you will have just, all you need to do is reverse this jump by right clicking, and then here edit this and reverse the jump. That will be the easy way to patch. But we don't want to patch, we want to actually fish out the password. So we are going to do password phishing. And interestingly, just before the jump left or right, you can see an interesting name, check password. So obviously this is the function which checks the password. And before the check password, you will see Rx moving something to RDI. So RDI is traditionally used for storing strings. RSI is for the source string and RDI is for destination string. So for sure we can make a good guess that probably check password parameter is RDI. So RDI will store the input string. So if you are going to run this, how are you going to run it? Because this obviously needs to be, the string needs to be entered from the console. 1, 2, 3, 4, 5, 6. And here, there will also be an output to the console. So how do you interact with the binary using cutter? That is the question. So in this lesson, I will show you how to do that. So in order to interact with this console inside cutter so that you can enter the string, you have to run it. So before you run it, you need to put a breakpoint. So a good place to put a breakpoint is obviously here, because we know that this is where the check password function is being called in order to check the input string RDI. So we can right click on this and then scroll down, select breakpoint, and then add breakpoint. Now we can run. So we can click on this button, start debug, click OK. There is no command line argument, click OK. And then down here, make sure this console is open. If you do not see this console, you can always enable it by going to Windows and clicking on console. Now down here in the previous lesson, I already taught you that there are two consoles, the reason console and the debugging input. So now we are going to use the debugging input. The debugging input allows you to interact with the console so that you can type in the password. So now what happens when we run this? So we click on this continue button until it hits the breakpoint that we have set. So click on continue, and straight away you see the console appearing down here, enter the password, and this console is a cutter console which has redirected this input. So now this interactive console is inside cutter itself down here. Enter the password as you can see. So in order for you to enter the password, you need to enable debug input, and now you can type the password 1, 2, 3, 4, 5, 6, and then hit enter. Alright, once you hit enter, it hits a breakpoint, and you can also confirm it here. Let's go to the graph view. It has hit our breakpoint. Okay, so this is how you can use the debugging input. So in the next lesson, I'm going to show you how to step into the function. So step into the function we have never used before. So I will show you how to do that in the next lesson. So far we've only done step over. So next lesson we'll start with step into. So in this lesson you already learned how to use the debugging input console in cutter. So that's all for this lesson. Thank you for watching. Hello and welcome back. In this video we are going to start with the debugging of the CrackMe, the new CrackMe. So as you have seen in the previous video, if we ran the CrackMe, it will ask for the password. If we enter an unknown string, just type 1, 2, 3, 4, 5, 6 and hit enter, it gives us this bad message, login failed. So let's open cutter, open our CrackMe, click OK, and straight away we can go to the main function over here and put a breakpoint here. This is where we will check for the password. So we can right click this and select breakpoint, add breakpoint. Now we are going to run the debugger, click OK, and now we are going to enable the debugging input and click run, and now it asks to enter the password. We enter 1, 2, 3, 4, 5, 6 and hit enter. It has hit our breakpoint. Let's go to graph view and step into it. So this is how we step into a function. You press this button to step into it and you will enter the function. If you wanted to go back and see the main function, just press the escape button. So the escape button will take you back out of it just to see where you were. And then to go back to where you are, just double click this function and now you're here, RBP. So we press step over, but before we do that, we want to enable reverse debugging. So we click this button, and so the step backwards button is enabled. Now we step over line by line. So nothing of interest here, we just step over until we come to some kind of comparison. So we step over. So this is the interesting thing here, which determines whether to go to the left or to go to the right. So what is it comparing? That's what we want to know. So let's step over until we reach here. Okay, so now it's going to compare RAX with RDX. We can see that RAX is 7 and RDX is 6. So this is a hint that is comparing the length of the string which you entered. Since we entered 1, 2, 3, 4, 5, 6, that's why we see 6 here. And then interestingly, RAX is 7. That means it is suggesting that you should enter 7 characters. We can test it out. So let's step over now. And then over here, set equals means that it will set AL to 1 if the result of the comparison is 0. So let's see that happening. Now AL is not 1, therefore the comparison is not 0. Now when you have CMP RDX, comparison means you take RDX minus RX. So if you minus this and this, you get 0. Then AL will be set to 1. That's the meaning of set E. So in this case here, we see that AL is not 1. Therefore, the result of the comparison is not 0. So now when it tests for AL, it is testing whether AL is 0. So if AL is 0, that means it's bad. Something went wrong. So AL should not be 0. So if you step over, so if something went wrong, it should go to the right. So let's confirm this. If you go to the right, it means it's quitting all the block of code. It's bypassing the entire block of code. Overseas. See this? This is bad news. Whenever there's a bypass like this, a shorter path, it's always the bad news. So as it is, I think it's going to bypass, and it's going to go right. So let's see. Yes, now it's here. So that means it has bypassed all this block. So that suggests that AL should not be 0. So in order for AL not to be 0, RDX must be 7. So when you take 7 minus 7, then you will have 0. So when it's 0, then AL will become 1. So now we can restart the program. We know that the minimum password length should be 7 characters. So we 2, 3, 4, 5, 6, 7. We type our notes here. So now we stop everything and we have to quit this program and restart again. Quit, close without saving, and reopen. Right, so that is necessary because otherwise there will be some process left in the memory which will prevent cutter from behaving correctly. So we have to quit and start again, and then select this, open, click OK. And now we do the same thing. We go to the main function, we put our breakpoint on check password. Then we run, click OK, click OK. Change this to debugging input and click run. And now it asks you to enter the password. This time we enter 7 characters. 1, 2, 3, 4, 5, 6, 7 characters. Press enter. It hits our breakpoint. Go to graph view, step into it, and turn on reverse debugging and step over. Keep on stepping over until it comes to our comparison again. Okay, this time you will notice that RAX and RDX are both 7. So that means when it compares, if it takes RDX minus RX, you will get 0. So because the result is 0, set E will set AL to become 1. And we look here, true enough, it becomes 1. So the test AL will fail because AL is not 0. So because it's not 0, it will not jump to C8, 3C8. It will go straight. See that? It went straight. So with that, we have found the actual required length for the input string. So we will end here and continue in the next lesson. Thank you for watching. Welcome back. So we will continue where we stopped. So the last lesson we stopped here, where we found that we entered the correct number of characters, which is 7, and it went straight. So now it went straight here. We are going to trace all the values inside these registers. So let's step over and see what is in RX. Right click this. Before that, let's change this to Reason console. So right click on RX, show in hex dump, and we find that it is 0. So we make a comment here and we say 0. I put a dash dash in front so that it's easier to identify our comment from Cutter's comments. So whenever you see dash dash means it's our comment. So RX is 0, we write comment there. So when you move RX to RDI, that means RDI is also 0. So I'm going to put another comment here. You can right click and click add comment, or you can use the shortcut key, which is semicolon. So I'll use semicolon. And then put a comment there and save that comment. So now RDI is also 0. So this is just to initialize the initial values. Step over. And then here it is creating a string. This is a basic string function that comes from C++. So it's just creating a string, that's it. So if you want to see what string is this, you notice that RX has changed its value. So we can show this in hex dump and you can see that it's 0. So it's creating an empty string. Then it's moving 0 to this location, 0, 1, 4. So we put a comment there as well. Okay, so this block is function is merely to initialize all the starting variables to 0. That's it. And create an empty string here. Next, let's step over. Step over and check what is inside EX. EX is 0. So we put our comment here again. 0. So here is 1, 4, EX, 0. And here it's going to compare. So it's going to compare EX and this. Now we know that EX is 0, but what is the value here? So to find out the value there, we can use the console. We type PX. And because this is a D word, so it's 4 bytes. And then use the add symbol, address symbol, and type RBP minus hex 1C. RBP minus hex 1C. Hit enter and you get 3. So px4 is to print the D word in hex form, and at this address RBP minus 1C, you see it is 4, it is 3. So we put a comment here, 3. So this is I think this is some kind of counter variable. Then it's going to compare these two. So the better command would be to type it in. Command is comparing EX, which is 0, with the value 3. So this is what it's comparing. So when it compares 0 and 3, it takes 0 minus 3 equals negative 3. So is it greater or equal to? No, it is not greater or equal to. So because of that, it will not go to the right. 3C8 means go over here. So you go to the left. So it's now on the left. At the moment, we don't know what is the purpose of this counter, but we have to step through line by line and trace the values in the offsets. Then we have a better understanding. So that's why the comments will help us, because we can see the previous values in the comments as we step through. So now it's going to move whatever is in here to EX. Let's step over. And we see EX has got the value 3. So we can put a comment here, 3. Now we minus 1 from EX. So we step over and see EX should become 2. And we can see EX is 2. So now we put a comment here as well. EX has become 2. Now it's going to compare this with EX. So what is this RBP minus 1 for? From here we know it is 0. So, and we know that EX is 2. So it is comparing 0 with 2. 0 from here and 2 from here. So let's put a comment. Comparing 0 with 2. So now it's going to take 0 minus 2, which should give you negative 2. So since it's not equal, jump not equal, it will go to the 3399, which is here. 3399, it will bypass this. See, it bypasses this. Jump over here. And then over here is moving this to EX, so let's step over. EX is 0. So put a comment there. Then it's going to move EX to RDX and zero out all the higher bytes to become zeros. That is the meaning of move XXD. So let's step over that. You can see it happening here. So let's see. Alright, you can see it became 0. So we can put a comment there. This also became 0. Then it's going to load this to RX. And you can see RX is address, not a value. We can show in hex stum. And we can confirm that it is an address because it starts with 7FFF. Remember, this is a little endian, so you read from the right to the left. And we know that in this program, the base address is 7FFF, as you can see here. So definitely this is an address, so you have to dereference this to find out what is stored there. So to dereference it, we have to put PX, put an R there. And addresses are all keyword, so we must put 8 for 8 bytes. And then to dereference it, we put an A symbol and then the RX register. Hit enter. And we see it stores the string DEC. So at this location, the RX contains the string DEC. put a comment there. So now we open Notepad or Notepad++, and we know that it's a 6 character, and then suddenly we see a string DEC, but we don't know what is the meaning of the string DEC. We have to go through the loop and trace it. So now this one is DEC. Step over. It's going to move RDX to RSI. So now RSI is here, RSI is 0. So we put a comment 0. So now we're going to step over this, move RX to RDI, and now we see what is in RDI. It's an address, so we right click, show in hexadump, and again we see there is an address. So this time we are dereferencing RDI. So this time we dereference RDI. So to dereference it, we put RDI here, and we see is DEC. So this one contains the string DEC. Put a comment there, DEC. Then we're going to step over. It's going to create something, the function call, but we don't know what this is, so we just ignore that. Then it's going to move one of the character in RX to EX. So let's see what it is. So we see that it's 64. So let's open the console and type RX. Use the RX tool to see what is the string 64, and we find that it is D character. So we can put our comment here. This is a D character. Then it's going to move AL to EX. So EDX. So EDX is also the D character. Put a comment there. D character. Then you will load this to RX. So let's step over. And we see now RX is this. Let's see that in hexadump. We see that it is address, so we have to dereference it like this, and we find that it is 0. So this one is 0. Put a comment 0. Next one, 0 could be the null terminator, or 0 could mean an empty string. So now EDX move to ESI, step over, and see what is in ESI. So ESI is the 4 lower bytes for RSI. So we see this is 64. So 64 is D. So this is also the D character. Put a comment there, D character. And then here we move RX to RDI, step over, look at RDI, show in hexadump. It is an address. So we dereference it down here, and we find it's also a 0 character, a null terminator probably. So we put a comment there. Okay, next is going to call this function, and then it's going to add 1 to RBP minus 14. RBP minus 14 is 0. Now we add 1, it should become 1, I think. So let's confirm that. Let's type the value stored at RBP. It's a D word, so you need to put 4. RBP minus 14. px4 RBP minus hex 14. So presently it's 0. So now after we step over, it should become 1. So let's repeat this command, and it became 1. So now we put a comment here. The value now at this offset is 1. So now we know RVP minus 14 is 1. So it's going to jump back up over here. So this is a loop, yes? So now this RVP minus 14 is 1 because we just increase it over here to become 1. So we can update this one. Previously it was 0, so we press semicolon, put a space bar and type 1 beside it. Okay, so this has a useful, it has a useful purpose. We can see the previous value and the current value separated by a space. And then here is going to compare EX with 1C. So what is EX? So we know that EX is 1 because from here it moved the value of this into EX. So we know that it is 1. Okay, so now we step over this, we will see EX becoming 1 and we see RX is 1. Alright, and then from here it's going to compare EX with this. So EX we know is 1. So it's going to compare 1 with this value, 1C. So what is 1C? So 1C should be 3, right? Because that was the previous value, but to confirm it, we can print out 1C. And you can see it's 3. Okay, PX4, because it's a D word, so we use 4. So 1C is 3. Still 3, has no change, but EX is now increased from 0 to 1, so it's comparing 1 with 3, so we have to update this. So previously it was comparing 0 with 3, now it's comparing 1 with 3, so you just put a space bar there to separate the first previous value with the current value. Click OK. So now it's comparing 1 with 3, previously it was comparing 0 with 3. And now it's going to check whether it's greater than or equal. In this case, it's not, because 1 and 3, 1 is less than 3. So 1 is not equal to 3. Neither is 1 greater than 3. So it's going to go to the left. So let's see, go to the left. Let's continue. So now it's going to move this to EX. So I think we'll stop this video here and continue with the next lesson, where we will continue from here where we stop. See you in the next one. Welcome back. So we continue from here. So next thing is comparing EX with this, and EX is 1 and RVP minus 1C should still be 3. Let's confirm that. RVP minus 1C. Okay, RVP minus 1C should still be 3, correct. So we update this. So now it's comparing 1 with 3. So we put a space to separate the previous argument. Previously it was comparing 0 with 3, but now EX has become 1, so now it's comparing 1 with 3. So using this form of commenting, we can keep track of the previous values for the parameters. So now EX, is it greater than or equal to RVP minus 1C? No, so it won't jump to this address, which is here. Instead it will go to the left. Now it's going to move, step over, and what is in EX? 3. Still 3. Next one, step over. Now EX subtract 1 becomes 2. So same, no change. Now it's comparing offset 14 with EX. So what is EX? EX is still 2, but what is this? RV minus 14. RV minus 14 should be 1. From here we know that. So it's comparing 1 with 2. So is 1 equal to or to 2? No, it's not equal to. Jump not equal to 2, you should not go straight, you should go here. This address. B239. So step over. Now it's going to move. This to EX, step over. And we see it is 1. So now this one, let's change the comment to become 1. Previously it was 0, now it's 1. Step over. So RDX also became 1. Step over. Now what's in RX is an address. Show in hex. Yes, it is an address. You can see here. So we dereference RX. We get DEC. So no change. Still holding the string DEC. Next is going to do this, step over. See what's in RSI. 1. RSI now becomes 1. Move this to RDI, step over. What's in RDI? Right click, show in hexterm. It's an address, so dereference it. Is DEC. Same, no change. So let's step over this function. It's just creating something, not sure what. So it's going to move 1 character. Byte means 1 character. Move 1 character from RX, this address to here, step over. And we see that the character is 65. So what is 65? 65 is E. So now the character is E. Previously it was D. So we can start tracing. Previously it was D. And now we saw it's moving an E character. So that's our comment, our notepad. Now we move this to EDX. So EDX also holds the E character. Next it's going to load this to RX. RX is address, so show in hexdump. Yes, it's an address. So you read this in reverse order, 7FFF, 7FFD and so on, because this is a little engine. And how we know this is the address? Because the base address for this binary is starting at 7FF. So when we see 7F like this, we know that this must be an address. So we need to dereference this RX. We find that 64. So 64 is, as we know, is the D character. So Let's update the comment. Previously it was 0, now it's D character. Let's step over and see what is in ESI. 65. And 65 is E character. Update the comments. DE. Now move RX to RDI. And let's see what's in RDI. Right click, show in hexdump. And it's address, so we have to dereference it. It's D character. 64, remember? 64 is a D character. So let's update the comments. Step over the call. So it's a operator plus equals. That means it's probably concatenating some strings. And then add 1 to this. So let's step over this. So after adding 1, it should become 2. Previously it was 1. So let's dereference. No, that's print out the value there. 1, 4. RB minus 1, 4 is now 2. So we update this comment to 2. Now it's going to go back up in the next loop. So it's going to go back up and come here. So RAP minus 1, 4 is now 2. As you can see from here, 2. So now I update this. So obviously this is a counter variable. It's previously 0, then it's 1, now it's 2. And now it's comparing this 2 with this value. So RV minus 1C, I believe, should still hold 3. So let's find out. Yes, it's still 3. So now you update this. It's comparing 2 with 3. So you see the usefulness of this style of commenting. You can compare the previous values. Previously it was comparing 0 with 3, and then 1 with 3, and then 2 with 3. So now is 2 greater than or equal to 3? Is this greater than or equal to this? No. So it will not go to the B368. It will still go left. So now it's gone to the left. Step over. EX is now 3. You can see from here. So same 3, no change. Minus 1, so it becomes 2. Confirm it. 2. Now it's going to compare this with 2. So what is RAP minus 14? You can see from here it's 2. So now it's comparing 2 with 2. So let's update the comment. Comparing 2 with 2. So is 2 equal to 2? Yes. So if 2 is equal to 2, what is going to happen? Will it jump here? No. Because GNE is true. Jump not equal. So jump not equal only will jump, it will go to this address down here. But because now it is equal, it's 2 and 2. This is 2, this is also 2, so it's going to go straight. Okay, step over. What is in RX? It's an address. Hexdump confirms an address, so we have to dereference the RX. Just press the up arrow key to get back the previous historical commands. And we see now is DE. So RX now stores the string DE. Put a command there, DE. So obviously DE is part of the password. It is reconstructing the password using the loop. So we can go back to our notepad and put a new note here, DE. Step over and check what is an RSI. Is an address. Show in hexdump. Okay, so hexdump shows that it's referencing the K character. This one is the K character. When you put a square like this, it is extracting 1 byte from here. So, and you can see here also K character. And to confirm that, you can actually dereference. We can actually look at RSI, dereference this address. So let's go to this, put RSI, and you can see K character. So it's pulling up the K character. Put a comment there, the K character. Now move this, let's type over. What is an RDI? Right click, show in hexdump, and it's address, so you have to dereference the RDI. You can see it's DE string. So now we can put a new comment here, the string DE, and that confirms this as well. DE, it is constructing the string and the password. It's going to call this function to append again. You can see this append operator. Step over it. Okay, then it's going to load this to Rx. So let's see what's that. Rx is here. Show next dump. Again, it's address, so you have to dereference Rx. And we see it's DEK. So now we have a additional K character at the back. So put a comment here. DEK. Okay. So now we know the password is being created. Now it's DEK. And then now we step on this, and then we see what is in RSI. It's an address, so show in hexdump, and now it's referencing the C character. You can see this C character is highlighted here. So to confirm that, we can dereference the RSI, and you can see it's a C character. So this one is a C character. Put a comment there. So we have the C character there. Now we move Rx to RDI, and let's check out RDI. It's an address, show in hexdump. It's also an address, so we have to dereference RDI. So we dereference RDI, and we find is DEK. So that also confirms this password, DEK. Now it's going to call another append operator here. Let's type over. Okay, so now it's going to go here and move this to EX register. EX is 2, so now this becomes 2. Step over this. RDX also becomes 2. Update the comment. Now load this to RX. So go to RX, right click, show in hexdump. Okay, RX is an address, so let's dereference RX, and you still see it's DEC, so no change, DEC. Step over. Now let's what's in RSI? 2. So now this becomes 2. Let's update it. Now let's step over this. Let's see what's in RDI. Right click, show in hexagram. It's an address, so we need to dereference RDI. And we find it's also DEC. So no change, same. Now it's going to call this. I don't know what is AT. Doesn't matter. Let's step over. Now step over again. It's going to move one character from the string to EX. So let's see what is in EX. 63. So what is 63? 63 is C. C. Okay, so now it's extracting the C character. It's extracting the C character. So 63 is C. So let's update this. Previously it extracted the D character, E character, and then C character. Okay, now it's moving this to EDX. EDX also C character. So let's update the command. Now it's going to load this to RX. Let's step over. And let's see what's there in RX. Show in hexagram. And its address. So let's dereference the RX register. And we see is DEKCAR. Alright, so that seems like the password. So we update the command DEKCAR. Alright, previously it was null terminator 0, then D, and then DEKCAR. So this seems like a password. Now let's step over this. And let's see what is in ESI. ESI is 63, so 63 is C character. So it's a C character, so we edit the command C character. Now move RX RDI, step over. What's in RDI? Right click, show in hexagram. It's an address, so let's dereference RDI. Deck car. Okay, it's a string as well, so this also now has been updated to deck car. Alright, so the password is probably deck car. And then we call this function. So add 1, so it should become 3. So let's step over and we check the value where it is 3. One, 4, and indeed it is 3. So this one now is 3. Update it. So now the counter is increased to 3, and then it's going to jump back up to the next loop. So it's going to jump here, and we know now that this is 3 because we just came from here where it increased it by 1, it became 3. RVP minus 14. So RVP minus 14 is 3, so we update this. So it's moving 3 to EX. So EX is 3, so it's comparing 3 with whatever is here. So it's comparing 3 with whatever is here. This was previously 3 as well, so most probably it's still 3. So let's check it out to confirm. 1C, and indeed it is still 3. So it's comparing 3 with 3. So alright, so let's do that now. Edit a comment. Is comparing 3 with 3. Previously it compared 0 with 3, and then in the next loop it compared 1 with 3, and then in the current loop it's comparing 3 with 3. So is 3 greater than or equal to 3? Yes, so this is true. Jump greater than or equal, so it's going to go to this address 368 on the right. There you go, it's moved to the right. So it seems that it has finished constructing the password. So this might appear to be the loop that constructs the password. On the left, this is the loop. You can see, if I zoom out, there's a loop here. So this loop on the left is to construct the password, and if you have to guess, the right is to compare the password with the input string. So let's confirm that. So now it's moving this to Rx. Let's step over and let's see what is in Rx. So for that, we will continue with the next lesson. I'll see you then, where we'll continue from here. Okay, let's continue. Move Rx to RDI. Let's check what's in RDI. Right click, show in hexdump. So it's address, so let's dereference it. Let's dereference RDI. And we find it's our input string 1, 2, 3, 4, 5, 6, 7. So this is our input string 1, 2, 3, 4, 5, 6, 7. Then it calls this function. Not sure what it does, but it doesn't matter. It's an AND function. And then moves Rx to RBX. Let's see what's in RBX. Right click, show in hexdump since it's an address. And you can see it seems to be pointing to the null terminator. And here is 1, 2, 3, 4, 5, 6, 7 in front of it. So let's assume it's this string, the input string. Because we can see it here. And then it's going to move this to Rx. So let's step over. And let's see what's in Rx. Show in hexdump. And this one seems to be an address, so we have to dereference Rx. And we see it's 1, 2, 3, 4, 5, 6, our input string. So let's put our comment there. Then it moves Rx to RDI and step over. And let's see what's in RDI. Show in hexdump. And it's address, so let's dereference it. Let's dereference the RDI register. Same, it shows it's also a string 1, 2, 3, 4, 5, 6. So let's put a comment there. 1, 2, 3, 4, 5, 6, 7. Now it's going to call this function begin. I'm not sure what it does. Now let's start over this. It's going to move RBX to RSI. So let's see what's RSI. Okay, RSI is also our input string 1, 2, 3, 4, 5, 6, 7. Next is going to move Rx to RDI. Step over and let's see what's in RDI. Right click, show in hexdump. Alright, it's also 1, 2, 3, 4, 5, 6, 7. So let's put a comment there. Next is going to call another function to create some kind of string. And then it's going to move this to RDX. Okay, let's see what's in RDX. Show in hex dump. And this is address, so let's dereference it. Dereference RDX. And you can see the password DEKCARC, which is cracked in reverse. CRACKED, cracked. See that? So RDX now holds the actual password. Put a comment. There you go. Next is going to move this to RX. So step over. And let's see what's in RX. So RX is also a string. It's also an address. So let's dereference RAX. And we see it is our input string in reverse order. That means it has reversed our input string. So let's put a comment there. Okay, then it's moving RDX to RSI. RDX is actually this password. So when it moves it to RSI, RSI now contains the actual password. And then here it moves RX to RDI, step over. Now RX from here we know is our input string in reverse order. So when it moves RX to RDI, that means RDI now contains our input string in reverse order. So you can put a comment here. So now we have RSI and RDI loaded into stack, into the register. So now it's comparing RSI and RDI by using the comparison operator here, as you can see. So after that, let's see the result of the comparison. It should be in AL. Why? Because it's testing it. So let's see what AL is going to be. 0. So in this case here, the comparison returns 0. So obviously now 0 means false. That means the comparison failed because our input string is not the same as the actual password. So notice that it takes your input and reverse it and then compares with the actual password. So that suggests that whatever we enter should be also the reverse of the actual password. So the password is DEKCRC. So when we type it in, we should type from the back, CRACKED. So to test the hypothesis, you can try it now. You can make a copy of your crackme and put it in a temp folder. So I already done that. I got a temp folder here containing a copy of crackme. So I go to my temp folder. Don't run the original crackme because it is loaded in your cutter. Make a copy and run the copy. So let's try the copy and enter a password in reverse, CRACKED, and login successful. So we have managed to phish the password. So this is how we can do phishing using the tracing of the register, and it's a very tedious process, as you can see. So it requires a lot of patience and need to be very careful when you're doing this. So the technique is to put comments like this as you trace through, you put the comments like this. And the comments, all the arguments are separated by spaces so that you have a record of the previous values. That way, when you read through your comments, you can understand the algorithm. You can even derive the algorithm, and you can figure out what it's trying to do just by looking at all the comments here, like this. See that? So by here, he already got the password, and then when he went to the last append, it added the last C to the back here. So it became DEKCAR C at the back. That's why when it came to the right here, it already got the complete password when it came to this part here. When you loaded it to RSI, you could see the last C was added. Alright. So just to make it complete, let's go through this and see what happens. So let's step over. Now test AL is 0, so that means obviously the AL should not be 0. If it's 0 means bad news. So we're going to put a comment there, should not be 0. So if it's 0, in this case AL is 0. Let's step over. AL is 0. So 0 means bad news because it is going to jump to the right and move on to EBX. That means this path is a bad path. EBX should not be 1. EBX should be 0. Let's see what happens now. So it's going here. We know the EBX is 1, so we can put a comment 1. When we are debugging, we just need to read our comments in order to understand the logic. See all the comments, I've got two dashes in the front so that we can differentiate it from Cutter's comments. So we just look at 2 dashes, all the comments there, and we can follow what's happening. That's why we put comments with 2 dashes in front. Same here. So now EBX is 1. It's coming here. It's loading this to RX. And what is RX? So let's dereference RX. And we see that it is a password. So why is it loading the password to RX? The clue is here. This symbol is to clean up the string. We have a basic string constructor, and we also have something to clean up the constructor. So we have this symbol like this. So it's cleaning up the strings. Alright, so it's not important. So this one, if we want to put a comment, we can put. So it's loading the string, and then it's moving the string to RDI. So RDI also has this string. And now it's going to clean up the string. And then it's going to compare whether EBX is 1. And we know from here that EBX is 1 because this is the path we took. And we know that the path we took is the bad one because our password didn't match. So when it's comparing this, it is going to be true. So here jump not equal, it's going to be false. So it's going to go straight instead of here. The good path is this one. It's supposed to jump not equal, right? But because EBX is 0, EBX is 1, so 1 minus 1 is 0, so jump not equal is false. It's going to go here, straight. See that? It's going to move this to this. So here, we put a comment, 0. So we know that R12 is another register in the 64-bit processor. 64-bit processor has got all these additional registers, R8, R9, 10, 11, 12, 13, 14, 15, and so on, which is not there for the 32-bit register. These are only available in the 64-bit register, 64-bit CPU. So because this is a 64-bit binary, so it can make use of these registers in the CPU. That's why you see this symbol R12. The D here means it's a lower 4 bytes. If it's just 12, then it's a full 8 bytes. So now it's going to do this, load this to RX, and what's in RX? We can dereference RX, and we see it's DEC, and again it's going to clean up the string. That's why it's loading that DEC string. Put a comment there. Again, it's moving the DEC string to RDI. So let's step over, put a comment, and it's going to clean up this string over here. So this is a parameter. RDI is a parameter for this cleanup function. Finally, it's going to move R12 to EX, and we know that R12 is 0. So EX is going to be 0. So this is 0. So he's going to go straight and return 0. See? EX is 0. So this function call returns 0. Check password returns 0. And that 0 is returned in EX. So every function normally returns the value in EX. So the result of the execution of function is normally stored in EX. So same thing here. It returns the result of this execution in 0. So 0 means bad news. Okay, 0. 0 means bad news. That means you got it wrong. If you got it right, it shouldn't return 0. It's probably going to return 1 or some other value. So let's see now. Let's step over and see what happens. Step over, it goes back to the main function. We step into this function, and now we come back here, and now outside this function. And it's going to test AL. And AL, we got 0 because call check password return 0. So 0 is bad news. Alright, so this one, we can put a comment, say should not be 0. So if you want to patch this, you can just patch this to be 1, or you can reverse this. But since we are doing phishing, we are not patching, we are phishing a password. Okay, so let's step over. So because AL is 0, it's going to go to the right and show the login field message. So keep a lookout on the bottom here. Goes to the right, and now we step over and we run all the way, and we say login field. Alright, so that confirms that our password is indeed this one, correct. Okay, so this completes the step by step of how we use the analysis of the registers to fish out the password. So that's all for this video. Thank you for watching. Congratulations on completing the course. Thank you once again for taking this course. Please remember to keep me updated on your progress or anything else that I can help you with. Meanwhile, here are my other courses which might interest you. Number 1. Learn ethical hacking by hacking real websites legally, Part 2. Learn ethical hacking by hacking real websites legally, Part 1. Internet of Things, IoT, Robotics, and Hacking with Node MCU. How to monetize your Construct 2 games using AdMob Ads 2020. Android mobile app development with Onsen UI and PhoneGap. Monetize your mobile PhoneGap apps using AdMob Ads 2020. Create mobile app icons using Inkscape. That is all from me, and I wish you all the best and hope to see you again in my future courses. Thank you.